There is a number in cosmology that should not care where we are. Not really. Not in any deep sense. If the universe is expanding, then the rate of that expansion is supposed to describe the universe itself, not our neighborhood, not the particular arrangement of galaxies around the Milky Way, not the accidental geography of our corner of space. A universal law should not feel provincial. And yet one of the strangest problems in modern physics begins with exactly that discomfort. When astronomers measure how fast the nearby universe is expanding, they get one answer. When they infer that same expansion from the early universe, from the relic light left behind when the cosmos was still young, hot, and almost violently simple, they get another. The numbers are close enough to sound almost trivial to anyone outside the field. But in cosmology, this is not a cosmetic disagreement. It changes the size of the universe we think we inhabit. It changes the rate at which structure formed. It changes how we connect the ancient sky to the one above us now. Worse than that, it has survived. This is what gives the problem its force. If one side were crude, or careless, or obviously broken, the tension would have dissolved into ordinary scientific housekeeping. But the measurements have become sharper. The methods have become more disciplined. The instruments have improved. And still, the mismatch remains, like a crack in glass that does not spread, does not vanish, does not explain itself, but keeps catching the light. There are only so many ways to interpret something like that. One possibility is that one of the measurements is wrong, not fraudulent, not foolish, just vulnerable to some hidden systematic error, some unnoticed bias buried inside calibration, distance ladders, dust, brightness, motion, or assumption. Science is full of ghosts like that. Numbers often look fundamental right up until they collapse into bookkeeping. Another possibility is more dramatic, that the standard model of cosmology, successful as it has been, is incomplete, that something in our description of matter, radiation, expansion, or gravity is missing, that the universe is not merely difficult to measure, but more complicated than the framework we have been using to describe it. But there is a third possibility, quieter and more disturbing than either. The universe may not be giving two different answers. We may be asking from the wrong place. That sounds, at first, like a philosophical maneuver, a way of retreating from physics into perspective. But it is not. It is a brutally physical idea, because the cosmos is not smooth. Not really. Not at the scales that matter to galaxies and clusters and the deep architecture of structure. Matter did not spread itself with perfect democracy. Over billions of years, gravity pulled the denser regions denser still, filaments thickened, clusters grew heavy, walls of galaxies emerged across unimaginable distances, and between those structures, space opened into vast underdense regions, cosmic voids where far less matter gathered than the average would lead you to expect. Not empty, just thinner, weaker, looser, places where the cosmic web relaxed its grip. And there is growing reason to suspect that the Milky Way may sit inside one. Not a small local dip, not a mere patchiness in the nearby sky, something far larger, a broad underdensity in our cosmic neighborhood, extending across scales so immense that the word neighborhood begins to sound absurd, a region with fewer galaxies, less matter, and therefore a weaker gravitational pull inward than the average universe around it. If that is true, then where we are stops being a harmless background fact. It becomes part of the measurement. Because expansion is not observed in abstraction, it is inferred through light, distance, motion, recession, brightness, redshift, signals traveling through a lumpy universe from one physical place to another. And if our region of space is unusually underdense, then local matter is not slowing outward motion in quite the same way denser regions do. Galaxies around us can acquire an extra drift outward. Distances and velocities can line up in a way that makes nearby expansion look slightly faster than the deeper average. The number is not forged. The observation is not fake. It is simply local truth wearing the mask of universal truth. That is the possibility this story turns on. Not that the universe is broken. That would almost be easier. A broken theory can be replaced. A failed measurement can be repaired. But a biased vantage point is more intimate than that. It means the observer is not standing outside the problem. It means the instrument includes the location. It means we may have mistaken a property of our surroundings for a property of reality itself. And that is what makes this more than a technical dispute over one cosmological parameter. It becomes a question about how any embedded intelligence measures the whole of the system it is trapped inside. Because we do not observe the universe from nowhere, we observe it from here, from inside a galaxy, inside a local flow of motion, inside a history of structure formation that did not distribute matter evenly and did not owe us a central, neutral platform from which to take our measurements. The ideal version of cosmology imagines something close to a clean external view, a description of the universe that rises above all local accidents. But the actual practice of cosmology begins in a place. It begins under a specific sky. It begins inside a specific gravitational environment. It begins with whatever kind of cosmic terrain happened to form around us. Most of the time, that fact can be managed, corrected for, folded into uncertainty budgets and statistical assumptions. But every so often, the universe pushes back. Every so often, it reminds us that local structure is not mere clutter laid on top of a clean background. Sometimes the clutter is large enough to deform the background we think we are seeing. Which leads to the first fracture in the comforting picture. We like to imagine that the large-scale universe, once averaged over enough distance, becomes smooth enough for perspective to stop mattering, that the local mess washes out, that somewhere beyond the nearby irregularities lies a clean cosmological truth waiting to be read off the sky like a stable number from a dial. But what if the dial itself is mounted on a moving wall? What if the local universe around us is not representative at all? What if our region is unusually thin, unusually quiet in one specific gravitational sense, and the very act of measuring expansion from within it gives the cosmos a slight but consequential tilt? Then the problem is not merely that the answer is hard. The problem is that the question was never as location independent as we wanted it to be. That is the deeper unease behind the so-called Hubble tension. Not just that two methods disagree, but that one of the most foundational numbers in cosmology may be sensitive to a hidden fact about our own address in the cosmic web. And the more familiar the sky appears, the easier that hidden fact is to miss. Because voids do not announce themselves the way planets do. They do not glow. They do not explode. They do not arrive in the telescope as obvious wounds in the dark. A void is measured indirectly, through missing matter, altered counts, subtle flows, deficits that only emerge once enormous maps are built and compared and corrected and distrusted and rebuilt again. You do not simply look up and see that you are inside one. You infer it, patiently, reluctantly, which is part of why this idea remained, for so long, easy to underestimate. If we were sitting beside some luminous catastrophe, no one would struggle to believe our environment mattered. But cosmic underdensities are quieter than that. Their force lies precisely in their subtlety. They do not break the visible sky. They bias the interpretation of it. And once you understand that, the question changes. It is no longer just, how fast is the universe expanding? It becomes, how much of that answer belongs to the universe, and how much belongs to the place from which we asked? Because if our region of space is unusually empty, then emptiness is no longer the absence of the story. It is the mechanism that begins it. Because the unsettling part is this: emptiness can move things. Not the way a force field in fiction moves things, with visible waves or dramatic impact. More quietly than that, more lawfully. In cosmology, matter is never just what exists. It is also what shapes the motion of everything around it. Galaxies do not drift through neutral scenery. They move through a landscape whose valleys and gradients were carved by the uneven distribution of mass. Dense regions pull inward. Thin regions fail to pull enough. Over vast stretches of time, that failure becomes motion of its own. A void is not powerful because it contains something mysterious. A void is powerful because it does not contain enough. That sounds almost too slight to matter. A negative statement, a subtraction, less matter here than average, fewer galaxies across some enormous volume, a shallower gravitational environment, but over hundreds of millions of light years. Less stops being small. A reduced inward pull across that scale means matter tends to stream away from the underdense region toward denser walls and filaments around it. The void does not need to push. The rest of the universe does the pulling, and what remains inside the underdensity responds accordingly, drifting outward relative to the deeper average. This is one of the quietest violent things in cosmology. A landscape can change your motion without ever touching you. Imagine standing in a broad basin after most of the weight has been removed from the ground around you. There is no sudden lurch, no audible fracture, just a subtle change in how everything settles, where motion accumulates, where trajectories gently lean. On human scales, it would be imperceptible. On cosmic scales, left alone for billions of years, it becomes a measurable pattern. That pattern is the first reason a local void matters. The second is more dangerous. Because astronomers do not measure the expansion of the universe by placing rulers directly across intergalactic space, they infer it from light arriving at Earth after long journeys through structure, motion, gravity, and time. A galaxy's redshift tells part of the story. Its distance tells another. Compare the two across many objects, and you begin to reconstruct the local behavior of expansion. But that reconstruction assumes something crucial, that the galaxies you are using are participating in the general expansion of space in a way that is not too badly contaminated by local peculiar motion. And this is where the underdensity stops being scenery and becomes a source of bias. If we live inside a region with less matter than average, then nearby galaxies are not only riding the overall expansion, they can also carry an extra component of motion caused by the local gravitational environment, an outward drift away from the underdense interior toward denser cosmic structure beyond it. That added motion does not announce itself with a label attached. It appears inside the very measurements used to infer how quickly the nearby universe is expanding. Which means a local void can make expansion look faster than the global universe truly is. Not by faking data, by bending interpretation. That distinction matters. It is the difference between error and entanglement. An error can be removed and forgotten. Entanglement means the thing you want to know is braided together with the conditions under which you are allowed to know it. The number is still real. The observations are still real. But they may be real in a local sense before they are real in a universal one. This is why the idea is so hard to shake once you have seen it clearly. At first, the proposal sounds like a rescue mechanism, a convenient patch, a way to soften an embarrassment in the standard cosmological picture by blaming our neighborhood. But that is too shallow. The deeper point is not that the void conveniently explains a discrepancy. The deeper point is that cosmology, despite all its mathematical elegance, remains an observational science conducted from inside the very structure it studies. The sky is not presented to us as a pure theorem. It arrives filtered through a position, and position has consequences. The universe on the largest scales does appear remarkably uniform when you zoom far enough out. That broad smoothness is not an illusion. It is one of the great triumphs of modern cosmology that such a violent, clustered, filamentary cosmos can still be described by a relatively simple large-scale model. But there is a dangerous psychological habit hidden inside that success. Once a model becomes powerful enough, it becomes tempting to imagine the messier local universe as mere noise, a perturbation around the real thing, not something capable of quietly reshaping the answer. Yet local structure is not cosmetic. It is made of the same gravity, the same matter, the same history that built everything else. And if a sufficiently large underdensity surrounds us, then the line between local complication and cosmological consequence is no longer clean. The visible sky does not make that easy to feel. Look upward on a clear night and nothing announces deprivation. The stars do not thin out in a way the naked eye could ever diagnose. Even galaxies, once plotted in large catalogs, do not organize themselves into a wound obvious enough to satisfy intuition. Space looks full enough, continuous enough, seamless enough. That continuity is deceptive. Distance flattens structure, perspective hides scale. The farther the pattern extends, the harder it is to see from within. Which is one of the most treacherous facts in this whole story. A void can be enormous without feeling dramatic. It can contain galaxies, clusters, even It can host normal astronomy, ordinary skies, ordinary local life. Its defining feature is not absolute emptiness, but relative deficit, less matter than there should be. Given the cosmic average, less gravitational braking, less pull inward, less resistance to outward flow. The result is not theatrical absence. It is a subtle reweighting of motion and density that only begins to emerge when you compare wide surveys across large depths and ask whether the matter around us is really as representative as we have assumed. The answer, for a long time, seemed likely to be yes. Not because anyone proved our local region was perfectly typical, but because the cosmological principle exerts a kind of emotional gravity of its own. It is elegant, useful, usually justified. The universe, averaged on large enough scales, should not privilege our location. We do not live in a specially chosen center. We do not occupy a cosmically favored seat. Those instincts are healthy. Science had to fight hard to escape the older narcissisms of human centrality. But there is a subtle difference between not central and statistically ordinary in every observationally relevant way. The first is a philosophical correction. The second is an empirical claim. And empirical claims can fail. This is where the local void idea acquires its real pressure. It does not ask us to return to a pre-scientific fantasy in which Earth occupies some mystic center. It asks something more disciplined and more unsettling, whether our location, though not metaphysically special, may still be physically unrepresentative enough to matter for precision cosmology. Not unique, not chosen, just inconvenient. A bad place from which to mistake the local slope for the shape of the whole landscape. Once that possibility enters the story, the Hubble tension changes character. It stops being a sterile disagreement between two methods and becomes a drama about scale. One set of measurements leans on the nearby universe, on calibrated distances, on objects whose light reaches us through the late-time structure around us. The other reaches back to an earlier epoch, to a universe before galaxies, clusters, and voids had matured into the architecture we now inhabit. One answer comes from the universe after structure, the other from the universe before it. And if our local structure is anomalous enough, then the disagreement between them is no longer mysterious in the same way. It becomes legible. That does not make it solved. Far from it. The hard part begins there. Because once you suspect the local universe may be biased, you have to prove it. Not with mood, not with plausibility, but with maps, with galaxy counts, with redshift surveys, with careful reconstructions of how matter is distributed around us and how that distribution changes with distance. You have to measure an absence vast enough to distort the expansion rate, while standing inside the very absence you are trying to diagnose. And that is a much stranger observational problem than it first appears. Because a void is not something you simply discover like a planet. You discover it by noticing that the expected universe does not arrive. Not as a single dramatic absence, but as a statistical wound, a thinning where there should have been more, a shallower density field than the larger cosmological average would lead you to expect. The evidence accumulates in counts and comparisons, in how many galaxies appear at different distances, in how matter seems to distribute itself, as surveys push farther out from the Milky Way and begin to ask a simple but dangerous question. Is our neighborhood normal? That question sounds smaller than it is. It sounds like bookkeeping. It is not. Once precision cosmology began to depend on mapping enormous populations of galaxies across wide volumes of space, normal stopped being a vague comfort word and became a measurable condition. If the local universe contains roughly the average cosmic density, then the sky around us should, after enough careful correction, blend into that expectation. If it does not, then the observer is sitting inside structure that may leak into the measurements used to describe the whole. And that is where the trouble began. Because when astronomers started comparing galaxy densities over large scales, some analyses found a persistent deficit in the nearby universe, a broad underdensity extending far beyond the local group, far beyond the easy language of our galactic neighborhood, reaching into a realm where local irregularity starts to become cosmologically relevant. Not empty space in the ordinary sense, not a vast black gulf stripped clean of all matter. Something more subtle than that. And in some ways more disturbing, a region that still contains galaxies, still looks like part of the ordinary universe, but contains fewer of them than it should. Enough fewer, perhaps, to matter. This is one reason cosmic voids are so conceptually treacherous. Human intuition is badly tuned to relative emptiness. We hear the word void and imagine an obvious absence, some clean, dramatic hole one could point to. But large-scale structure does not usually arrange itself with that kind of theatrical clarity. The cosmic web is textured, hierarchical, noisy, alive with gradients. Underdensities come with filaments crossing them, clusters bordering them, galaxies scattered through them. The eye sees continuity. The statistics reveal shortage. And shortage, on these scales, is not innocent. To measure it, astronomers count galaxies at different depths and compare those counts to what a representative universe should produce. They correct for survey limits. They correct for selection biases. They correct for the fact that dimmer galaxies vanish from catalogs as distance increases. They try to separate genuine structure from the distortions introduced by observation itself. It is patient work, unromantic work, the kind of work that almost never looks cinematic from the outside. And yet, buried in those counts is the possibility that our local cosmic environment is thinner than the standard story would prefer. This is why the issue never reduced cleanly to one paper or one claim. The difficulty is not merely whether a deficit exists. The difficulty is scale, shape, depth, and significance. How large is the underdensity? How far does it extend? Is it roughly spherical, or lopsided, or part of some more tangled larger pattern? Does it fade smoothly into the average cosmic density, or does it break in stages? Is the apparent shortage truly physical, or partly an artifact of how we infer distances and select galaxies? These are not decorative complications. They determine whether the structure is mildly interesting or cosmologically consequential. And the most unsettling version of the answer is not that our region is bizarre in some flamboyant way. It is that it may be just biased enough to matter. En indobekmundisi is bar. There is a peculiar cruelty in that. If the evidence were overwhelming and grotesque, the field could reorganize around it. If it were weak and incoherent, the idea would die. But the most intellectually dangerous problems live in the middle, plausible enough to survive, uncertain enough to resist closure, large enough to influence interpretation, subtle enough to remain arguable. The local underdensity sits in exactly that territory. By the time this possibility entered serious cosmological conversation, the emotional grammar of the field had already been shaped by a deeper assumption that whatever small-scale messiness the late-time universe contains, there exists some scale beyond which the average picture becomes clean. That assumption was not foolish. It remains one of the most successful intuitions in the entire discipline. The large-scale universe really does become statistically smoother as you zoom out. But smoother is not the same as neutral. And one of the recurring mistakes of successful theories is that people begin to trust the smooth limit more than the rugged path by which observations actually reach it. We never measure the smooth limit directly. We infer it from inside the ruggedness. That is what makes the underdensity such a powerful disturbance in the story. It attacks not the equations first, but the comfort behind them. It suggests that the observer's surroundings may remain relevant longer, across larger volumes, and with more subtle consequences than intuition would like. And the farther those consequences extend, the more uncomfortable a new possibility becomes. What we took to be a universal background may be, in part, local terrain. It is worth slowing down here, because the psychological temptation is to flatten the whole issue into a slogan. We live in a giant void. The phrase is vivid. It travels well. It sounds like a revelation, but stripped of nuance, it becomes misleading. The real force of the idea lies not in melodrama, but in calibration. We may inhabit a region whose matter density is below the cosmic average by enough to alter motion fields and bias nearby expansion measurements. That sentence is colder than the slogan. It is also more dangerous. Because once you say it carefully, the consequences proliferate. If galaxy counts around us are systematically low over a large enough scale, then the gravitational landscape around the Milky Way is not quite what a representative patch of the universe would provide. If the gravitational landscape is off, then local velocity flows are off. If local velocity flows are off, then redshifts in the nearby universe do not map cleanly onto pure expansion. If those redshifts help anchor the local expansion rate, then the number we infer from them may inherit part of that environmental bias. One deficiency unfolds into another. Not error cascading into failure, context cascading into interpretation. And that distinction matters because it preserves the dignity of the measurements even while unsettling their universality. The astronomers are not fools. The telescopes are not broken. The data are not counterfeit. The sky is simply more entangled than the clean version of the story allowed. A local void, if large enough, does not humiliate cosmology by exposing incompetence. It humbles cosmology by exposing embeddedness. The observer is inside the apparatus. Even now, there is no simple consensus, because consensus would require the structure to become indisputable in both observation and consequence. Some surveys support a significant local deficit. Others complicate the profile. Some analyses suggest the effect could ease the tension in the expansion rate. Others argue it cannot do enough on its own, or not without invoking a structure larger or cleaner than the standard cosmological picture comfortably produces. The disagreement itself is telling, not because science is lost, but because this is what reality looks like when the signal sits close to the scale of the assumptions used to interpret it. And there is an irony buried in that. The more sophisticated cosmology becomes, the more it discovers that where we are cannot be treated as a philosophical embarrassment left behind with geocentrism. That older mistake was believing we occupied the center of creation. This newer vulnerability is subtler, believing we do not occupy any observationally inconvenient place at all. Those are not the same error. One flatters human importance. The other overestimates human neutrality. The universe owes us neither. It does not owe us a central seat. It does not owe us an average one. It does not owe us a clean observational platform from which local structure politely cancels out. We emerged where matter happened to cool, clump, enrich, and build galaxies. The resulting location may be unexceptional in the broad metaphysical sense, and still statistically awkward for precision measurement. That is a hard thought for science to metabolize, because science depends on the possibility of generalization. The whole ambition of cosmology is to speak about the universe as a whole, not merely about one strange patch of it, but the path to generalization is always local first. We begin with what reaches us, with light, with recession, with counts, with the sky our location permits. If that sky is biased, then the bias enters not as a vandal, but as a premise. And premises are hardest to see from within. Which is why the local underdensity matters even before it solves anything. Even if it turned out to soften only part of the expansion discrepancy, or to fail as a complete explanation, it would still have done something profound. It would have shown that one of the cleanest-looking disputes in modern cosmology could not be understood without taking our own environment seriously. It would have forced the field to admit that local is not always small enough to ignore. But before any of that can become a full argument, one deeper mechanism has to be faced, because it is one thing to say an underdensity exists. It is another to understand how such a thing can quietly reshape the very number at the center of the crisis. How can a region with less matter than average make the universe itself appear to expand faster? That is where the story stops being cartography and becomes dynamics. Because once emptiness changes motion, it begins to change time. Because once emptiness changes motion, it begins to change time. Not time in the dramatic sense people usually reach for. Not clocks suddenly malfunctioning. Not relativity turned into spectacle. More quietly than that. More mathematically, and therefore more dangerously. In cosmology, time and expansion are tied together so deeply that if you alter how matter is distributed across a region, you alter how that region evolves. Density is not just a description of what is present. It helps determine how strongly expansion is slowed, how structure grows, how motion accumulates, how the universe ages locally relative to the smooth idealization we like to write in equations. A denser region is a deeper gravitational well. Expansion there is more heavily braked. Matter falls inward more aggressively. Structure thickens faster. The local cosmic environment becomes dynamically heavier, not just visually richer. An underdense region does the opposite. It is not outside the universal expansion. Nothing local escapes that larger story. But because there is less matter available to tug inward, less gravitational braking, the region can expand a little more freely than the deeper average. Not infinitely, not arbitrarily, just enough that over billions of years, the difference stops being negligible. The void slowly runs ahead. That phrase matters. A void can run ahead of the background universe. Not because it is powered by some exotic, repulsive substance hidden in the dark, but because gravity is weaker there than average. Less matter means less resistance to outward separation. Galaxies embedded in or near the underdense region end up with what cosmologists call peculiar velocities, motions relative to the smooth Hubble flow, on top of the ordinary recession caused by cosmic expansion. Those extra motions are not random noise in the everyday sense. They are the kinematic fingerprint of structure. The cosmic web is not static architecture. It is a field of slow migration. And if we are inside a large underdensity, then some of the galaxies we use to measure the nearby expansion rate are not merely receding because the universe expands. They are receding with an additional local drift inherited from the fact that our environment is dynamically thin. That is where the number at the center of this story begins to tilt. To see why, it helps to strip the measurement down to its bones. The local expansion rate is inferred by comparing how far away astronomical objects are with how fast they appear to be moving away from us. Distance on one side, recession on the other. It sounds almost naive when stated that simply, but the entire elegance of the method depends on a dangerous assumption, that once you correct for known local motions, what remains is the clean imprint of cosmic expansion itself. But what if the known local motions are not local in the harmless sense? What if the region affecting them is not a small nearby perturbation, but a structure so large that it overlaps with the very scales on which we begin treating the sky as cosmological rather than parochial? Then the usual distinction starts to weaken. The measured recession speed includes a contribution from a wide underdensity-driven outflow. The distance ladder dutifully calibrates objects inside a region whose dynamics are already slightly biased. And the inferred expansion rate, while internally consistent, begins to reflect not just the universe but our position inside a gradient of density. A faster universe may be a shallower well. That is the compressed version. The full version is more delicate. Not every void-sized anomaly can shift the inferred expansion rate enough to matter. Not every local flow is large enough or coherent enough to survive the corrections astronomers already make. The effect depends on the void's size, depth, profile, and relation to the objects used in the analysis. That is why the idea remains debated rather than triumphant. But the mechanism itself is not mystical. It is one of the most natural things in the whole story. Change the density field, and you change the velocity field, change the velocity field, and you change what recession appears to mean. Change that meaning, and a universal constant starts to inherit local weather. This is why the local void idea is not a fringe fantasy pasted onto the edge of serious cosmology. It emerges from ordinary gravitational logic. The question is not whether such a mechanism exists. The question is whether the actual structure around us is large and deep enough for the effect to be consequential. It's spanned. It got stommed. That distinction is easy to lose when a story becomes publicly seductive. People prefer binary dramas. Either the void solves the Hubble tension, or it is irrelevant. Either the local universe is radically special, or the idea should be ignored. But reality is rarely kind enough to arrange itself into those clean oppositions. A void can be real without being decisive. It can influence the inferred expansion rate without fully explaining the discrepancy. It can soften the tension while leaving room for additional systematics, or new physics, or both. The world does not have to choose between theatrical victory and total dismissal. And that is part of what makes the situation intellectually hard. Because once a local underdensity becomes dynamically plausible, The Hubble tension stops behaving like a simple disagreement between two teams with two numbers. It becomes layered. One answer comes from the nearby, mature universe, from Cepheids, supernovae, and the late-time structure through which their light reaches us. The other comes from the infant universe, from relic radiation, from an epoch before galaxies and clusters and enormous voids had fully matured into the pattern that now surrounds us. One answer is extracted after billions of years of structure formation. The other is inferred from before that structure had time to carve large environmental asymmetries into the cosmic landscape. That asymmetry in epochs is not cosmetic. It means the two methods are not merely using different tools. They are looking through different universes in a meaningful sense. The early universe inference sees a cosmos before local terrain mattered to us in this way. The late universe measurement looks out from inside the terrain itself. If our region is underdense, then the comparison between those two answers is no longer just a test of instrument against instrument. It becomes a test of whether local structure has contaminated what we mistook for a global readout. And suddenly the whole problem acquires a new shape. Not, why are the numbers fighting? But, why did we assume they were answering the same version of the question? The local measurement asks, in practice, how the nearby universe behaves from within the actual gravitational environment we inhabit. The early universe inference asks what the expansion rate should be today, if the standard cosmological model correctly connects the ancient plasma to the present cosmos. If the present cosmos around us is environmentally biased, those answers may diverge without either side being foolish. The tension, then, is not simply contradiction, it is scale leakage, local truth bleeding upward into a universal claim. This is the dangerous possibility that makes the underdensity idea so hard to dismiss psychologically. Because it preserves too much competence, no one has to be incompetent for the conflict to survive. The distance ladder can be exquisitely calibrated. The cosmic microwave background analysis can be mathematically rigorous. Both can be telling the truth available from their own domain. What fails is the assumption that those domains are joined by a perfectly neutral observational bridge. The bridge may run through us. And if it does, the observer becomes part of the mechanism. That is a profound shift in tone. Up to this point, the story can still be heard as one more episode in the long history of astronomy, discovering that the universe is more structured than it first looked. But now, the emotional pressure deepens. Because once your own location enters the measurement chain, cosmology stops feeling like an external reading of reality and starts feeling like an inference performed from inside a current whose boundaries you are only beginning to map. It is one thing to be small in the universe. It is another to be situated. Smallness is humbling, situation is distorting, and that distinction lies at the center of everything that follows. The great dream of cosmology has always been to average over enough scale that local accidents no longer matter, to rise, mathematically, above the particular, to recover the universe not as seen from one galaxy, but as described from nowhere. The equations can often do that. The observations cannot begin there. They begin here, with light arriving at a planet inside a galaxy, inside a web of structure still moving under gravity's slow instruction. So, the real question is no longer merely whether a void surrounds us. The real question is whether our best universal number has been partially written by local geography. And once you take that possibility seriously, the Hubble tension ceases to be just a mismatch in cosmology. It becomes an accusation, not that the universe is inconsistent, that we may have confused proximity with truth. That accusation does not arrive all at once. It had to be earned, slowly, against the instinctive resistance of a field trained to distrust any claim that our location might matter too much. Cosmology had spent centuries clawing its way out of local vanity. Earth was not the center. The sun was not the center. The Milky Way was not the center. Even our galaxy was just one strand in a larger web. Every major correction moved us away from privilege. So, when a modern cosmological anomaly begins to whisper that our immediate environment may be distorting our view, the idea carries an unfortunate resemblance to older, more primitive fantasies. It sounds like a regression. But it is not a regression. It is something more disciplined, and in some ways more severe. The claim is not that we occupy a metaphysically special location. The claim is that we may occupy an observationally inconvenient one. That is a colder idea, less flattering, more scientific. The universe does not owe us a central throne, but it also does not owe us a statistically average platform from which its deepest properties become easy to read. There is no law that says intelligence must arise in a region optimally suited for precision cosmology. We emerged where star formation, heavy elements, chemistry, and time allowed us to emerge. Whether that location is clean for measurement is a separate question. And once you separate those questions, the underdensity stops sounding like philosophical contamination and starts sounding like a legitimate physical problem. This is why the local void hypothesis did not enter serious discussion as poetry. It entered through surveys, through counts, through the ugly, cumulative labor of mapping where galaxies actually are, and asking whether the matter around us looks representative on the scales where we had hoped representation would begin to settle in. The unease did not come from one spectacular image. It came from patterns that repeated often enough to become difficult to shrug away. A shortage here, a deficit there, a local density lower than expected across scales large enough to feel dangerous. None of those, by themselves, are cosmological thunder. Any one result can be overturned. Any one catalog can be incomplete. Any one correction can shift under new methodology. That is the ordinary churn of science. But the pressure rises when the same broad suspicion survives across multiple lines of analysis, that the nearby universe may be underdense relative to the larger cosmic average, and underdense not merely in a decorative sense, but enough to influence motion fields and therefore inference. This is where the story acquired one of its most important names. The structure often discussed in this context came to be known as the KBC void, after Keenan, Barger, and Cowie, whose work helped crystallize the argument that the local universe might contain a substantial underdensity on scales large enough to matter. The details have remained debated. The profile, depth, and exact significance are still contested. But the naming matters because names change the temperature of an idea. Once something is named, it stops behaving like rumor and starts behaving like a candidate feature of reality. And reality becomes harder to ignore once it can be pointed to. But even here, the temptation is to simplify too quickly, to imagine the KBC void as a kind of giant hollow bubble surrounding the Milky Way with clean edges and obvious emptiness. Reality is less cooperative than that. The actual large-scale universe is messy. Voids overlap, walls thicken unevenly, filaments thread through underdense regions. Any profile drawn around a local deficit is, to some extent, an attempt to summarize a structure more ragged than the summary. That is one reason the subject remains alive. A complicated environment can produce complicated measurements, and complicated measurements rarely die cleanly. Still, the basic intuition is straightforward enough to retain its force. Count galaxies as a function of distance. Infer luminosity densities. Compare the local inventory of matter to what a representative cosmic volume ought to contain. Keep correcting, keep checking, keep distrusting your own result. And then notice that the shortage does not vanish when you want it to. This is the part of science that rarely gets dramatized honestly. People like the moment of revelation, the graph, the impossible image, the sentence that rewrites the world in a single gesture. But most important anomalies do not begin that way. They begin with irritation, with numbers that refuse to align, with background assumptions absorbing strain longer than expected, with a result that seems too awkward to trust and too persistent to dismiss. The underdensity near us has lived in that uncomfortable zone for years. It has never become obvious enough to end the discussion. It has never become weak enough to leave it, which is exactly what makes it dangerous. A weak idea can be thrown away. A decisive idea can reorganize the field. The hardest ideas are the ones that remain plausible at just the level required to infect interpretation without commanding it. They do not settle the argument. They contaminate every version of it. That is what the KBC void did to the Hubble tension. Before the local underdensity scenario became part of the conversation, the tension could be staged in a simpler dramatic form, one number from the nearby universe, another number from the early universe. If they disagree, then either one method hides an error or the standard cosmological model is incomplete. Clean options, high stakes, a clear split. Once the possibility of a significant local underdensity enters, that split becomes more subtle and more treacherous, because now there is a way for the local measurement to be internally sound and still environmentally biased. The distance ladder can perform exactly as designed while operating inside a region whose matter distribution gives nearby galaxies an extra outward drift. The data can remain honest, the interpretation can remain careful, and the inferred result can still come out too high relative to the global background. In other words, the anomaly no longer needs incompetence to survive. It only needs geography. That is one of the most elegant and unsettling features of the whole story. We are used to scientific crises resolving into either correction or revolution. Either someone made a mistake, or nature is stranger than the model allowed. But the local void scenario opens a third category. Nature may be stranger in a quieter way, not because the law is wrong, but because the observer is embedded inside a structure that quietly bends the law's apparent value. The theory survives. The measurements survive. The observer becomes the problem. There is a certain cruelty to that realization. It preserves nearly everything the field takes pride in: precision, discipline, calibration, mathematical consistency. And yet, it shifts the center of discomfort from technique to situation. The better the measurements become, the less satisfying it is to blame sloppiness. The cleaner the analyses become, the more attention shifts toward the one element that cannot be sterilized away, where, in the late-time universe, the measurement is being made. That change in emphasis is what gave the underdensity idea so much staying power, not because it solved the whole problem, but because it transformed the emotional grammar of the problem. It made the Hubble tension feel less like a duel between data sets and more like a conflict between scales, between the universe as it looks from our evolved position inside late-time structure, and the universe as it must have been before that structure had finished sculpting itself around us. One answer emerges from the mature universe, the other from the infant universe. The gap between them may be, in part, the cost of living after structure. That is a beautiful sentence if left alone too long. So, it needs to be pinned back to mechanism before it starts sounding like atmosphere instead of argument. The actual issue is this: late-time structure formation creates inhomogeneities, clusters, filaments, voids, flows. Those inhomogeneities alter local motions. Local motions can bias the relation between redshift and distance used to infer nearby expansion. Early universe methods, by contrast, infer the present expansion rate through a model anchored in a much smoother epoch, before our local cosmic terrain had matured into what it is now. If our region is significantly underdense, then the late-time and early-time methods are not sampling the same effective environment. Their disagreement may therefore contain a real environmental component. That is the sober version. And the sober version is already destabilizing enough. Because once you grant even part of it, the observer is no longer a passive recipient of cosmological truth. The observer sits inside a structured region whose density profile participates in the very quantity being measured. That means local is not merely a nuisance to be corrected and forgotten. It may be an ingredient in the answer itself, which leads to a more uncomfortable possibility still. Maybe the most dangerous assumption in modern cosmology was never that the universe is simple. Maybe it was that our patch of it is irrelevant quickly enough. That assumption is easy to sympathize with. Without some version of it, cosmology becomes impossible. You cannot build a science of the whole if every local wrinkle remains sovereign forever. At some point, averaging must redeem you. At some point, the larger order has to emerge from the smaller chaos. And in a broad statistical sense, it does. But broad statistical truths can coexist with observationally awkward local realities. The universe can be homogeneous in the grand language of theory, while remaining annoyingly non-neutral in the practical language of measurement. This is the narrow ledge on which the KBC discussion stands. Not the claim that everything we know is wrong. Not the claim that the standard model has failed. Not the claim that we occupy a miraculous cosmic seat, something much harder to metabolize, that we may live in a region ordinary enough to produce life and astronomy, yet unrepresentative enough to distort one of the most important numbers in cosmology, a bad place from which to mistake the local slope for the shape of the whole. And once that possibility becomes structurally real, the tension between the two expansion rates changes again. It is no longer just a disagreement over value. It becomes a disagreement over what kind of truth each method is allowed to access. One method reads the universe through the nearby matter distribution that history left around us. The other reconstructs the present from an earlier, smoother cosmos. If the local terrain is biased, then both numbers can be meaningful without being interchangeable. That is the dangerous possibility. Not that one side is wrong, that both sides may be telling the truth available at their scale. And if that is true, then the Hubble tension is not yet the deepest problem. The deeper problem is that cosmology may have been speaking too casually about the expansion rate, as though the path from local observation to global truth were cleaner than the universe ever promised it would be. The phrase sounds clean until you hold it under pressure. The expansion rate of the universe. Singular, definitive, as if the cosmos were offering up one transparent number, waiting only for better instruments and tighter statistics, as if the problem were merely technical refinement. But once local structure enters the chain of inference, that singular language begins to feel less secure, not false exactly, just prematurely smooth, too confident that the road from here to the whole is flatter than it is. Because one of the reasons the Hubble tension became so disruptive is that it did not emerge from weak methods scraping at the edges of astronomy. It emerged from two of the most ambitious measurement programs in modern science, each reaching toward the same cosmic quantity through a fundamentally different route. One starts in the nearby universe. It is patient, layered, almost architectural in its logic. First, you calibrate the distance to relatively nearby objects, whose geometry can be known by direct methods. Then you climb outward to stars, whose intrinsic brightness can be standardized. Then, farther still, using supernovae that act as bright markers across cosmological distances. It is a ladder not because it is crude, but because each rung depends on the integrity of the one below it. By the time the measurement reaches the scale where universal expansion dominates, it carries with it the accumulated precision of everything that came before. The other route begins in a completely different epoch. Not with mature galaxies, not with late-time structure, not with the nearby sky at all. It begins with the cosmic microwave background, the relic light from a universe only a few 100,000 years old, when matter and radiation had finally decoupled and the plasma had gone transparent. That ancient light preserves the imprint of fluctuations from an earlier, denser cosmos. Analyze those fluctuations within the standard cosmological model, and you can infer what the expansion rate today ought to be if that model is the correct bridge from the early universe to the present. So, the conflict is not just between datasets. It is between temporal regimes of reality. One method reads the universe after billions of years of structure formation, after matter has collapsed into clusters, drained from voids, flowed along filaments, and carved the late-time cosmic web into its present form. The other reads the universe before any of that architecture had matured, before our local underdensity, if it exists as suspected, had fully become the environment through which nearby measurements must now pass. That difference is the whole wound. Because if the local universe around us is dynamically biased, then the distance ladder measurement and the early universe inference are not sampling the same effective cosmos. They are anchored to different stages in the universe's own development, one from a time before the terrain formed, the other from within the terrain itself. And that is how a single number starts to split. Not because the universe is indecisive, but because the universe is being approached through two different slices of its own history. This is the point where public descriptions often become too clean. They say one method measures directly, the other infers indirectly, and then move on. But the real asymmetry is deeper than direct versus indirect. The real asymmetry is environmental. The late-time route does not merely happen later. It happens after local structure has become capable of bending motion fields and therefore bending the interpretation of redshift. The early time root does not merely happen earlier. It happens before our local cosmic address had matured into a serious contaminant, which means the disagreement may not be one of truth against error. It may be one of truth against embedded truth. That possibility is more difficult to emotionally absorb than an ordinary mistake. A mistake reassures us that once found, the universe becomes cleaner. Embedded truth does the opposite. It says the universe can be lawful and still force every observation through a local filter. It says the problem is not that we failed to look carefully enough, but that careful looking itself begins inside a structure we do not control. And if that is true, the Hubble tension stops behaving like a crack in theory alone. It becomes a referendum on how far local correction can really take us. For decades, cosmology has relied on the principle that once you average over sufficiently large scales, the universe becomes statistically homogeneous and isotropic, not perfectly smooth in detail, but smooth enough that no single region should dominate the description of the whole. This principle remains one of the discipline's great stabilizing ideas. Without it, the mathematics becomes less elegant, the interpretation more dangerous, the generalization from observation to cosmology far more precarious. But a principle is not a pardon. It tells you what should emerge at the right scale. It does not guarantee that your measurements have reached that scale cleanly, nor that the path toward it is free of environmental contamination. A local underdensity does not overthrow the cosmological principle by existing. It exploits the distance between the statistical ideal and the observational route by which we try to reach it. That route, for the local expansion rate, is narrower than people intuitively imagine. We do not measure infinitely far. We measure what can be calibrated. We use objects whose distances can be trusted, whose properties can be standardized, whose redshifts can be compared meaningfully. But the useful universe for that task is still a finite region, and if that region overlaps with a significant underdensity, then local outflow is not some tiny irritant confined to the margins. It becomes part of the signal budget, a universal answer extracted through a regional window. This is why the underdensity idea keeps surviving even among people who remain unconvinced that it fully resolves the tension. It does not have to solve everything to change the problem. It only has to demonstrate that the local expansion measurement is more geographically entangled than the simple story allowed. Once that door opens, the Hubble tension is no longer a clean binary between bad data and new physics. It becomes a layered dispute in which environment, method, scale, and theory all overlap. And overlap is harder to dramatize than revolution. But it is often closer to how reality behaves. A field reaches crisis not only when a law fails, but when too many subtle effects begin to share responsibility for the same anomaly. The result is less cinematic than a single contradiction, but more intellectually difficult. One correction is manageable. A stack of partial corrections is destabilizing. If local structure explains some of the discrepancy, calibration systematics explain another part, and model limitations still explain another. Then the path to clarity becomes less like finding a broken bolt and more like untangling a cable buried inside the walls. This is one reason the Hubble tension has become so psychologically charged. It sits at the intersection of high precision and low innocence. The measurements are good enough that carelessness no longer feels like an adequate explanation. But the universe is structured enough that one clean answer no longer feels safe either. Cosmology has arrived at the uncomfortable stage where its own success forces it to confront how contaminated success can become by local conditions, which brings the local void idea into sharper focus. Because the real power of a void is not only that it changes galaxy counts or velocity fields, it changes what it means to trust nearby evidence. It inserts a quiet asymmetry into the late-time universe, the further expansion of an underdense region relative to the deeper background. That extra running ahead becomes part of the recession pattern we observe. And because local methods necessarily build upward from nearby calibrations, the environmental bias can propagate through the latter rather than staying politely isolated at the bottom. That last point is easy to underestimate. People hear local environment and imagine something that should wash out immediately, like weather averaged into climate, but a large underdensity is not weather, it is terrain. It sits beneath the measurement architecture itself. If the first rungs of the ladder are embedded in a region whose dynamics are not representative, then the later rungs inherit more than just distance. They inherit a frame. And frames are dangerous because they disappear into normality. Once you have lived inside one long enough, it stops feeling like a condition and starts feeling like reality itself. The nearby universe looks ordinary to us precisely because it is the universe we learned cosmology from. Its galaxy distribution, its flow fields, its recession patterns, its sky. All of this formed the intuitive background against which theory was tested. If that background is biased, then the bias is not just numerical, it is conceptual. It has been teaching us what normal looks like from the beginning. A void does not merely distort a measurement. It can distort the baseline from which distortion is recognized. That is what turns the problem from technical to epistemic. The issue is no longer just whether a certain density profile shifts the inferred value of the Hubble constant by some percentage. The issue is whether the observer has mistaken a local environment for a neutral launch point, whether cosmology, for all its sophistication, has still been relying on a hidden innocence, that our sky becomes representative quickly enough for confidence to outrun caution. Maybe it does. Maybe the effect is smaller than its most forceful advocates hope. Maybe the void softens the discrepancy but does not erase it. Maybe additional new physics still lurks behind the remainder. All of that remains possible. But once the observer's environment enters the story this deeply, even a partial effect becomes philosophically expensive. Because the dream of cosmology was never merely to gather numbers. It was to gather numbers that meant the same thing everywhere, once local clutter had been corrected away. A local underdensity challenges that dream at its most practical point. It asks whether we have been too casual about when clutter stops being local and starts becoming cosmological. And if we have, then the most dangerous sentence in the whole debate is not, "the model is wrong." It is this: both sides may be right, but one of them is speaking from inside a slope. Once that possibility becomes real, the Hubble tension ceases to be just a disagreement about value. It becomes a disagreement about representativeness, about whether the nearby universe is offering an honest sample of the cosmic whole or a subtly biased cross-section of it. And if it is the latter, then the problem is no longer merely how to reconcile two measurements. It is how to know when a local truth has become large enough to impersonate a universal one. That is the point at which cosmology becomes more than a science of expansion, or it becomes a science of perspective under structure. And halfway through that realization, the subject changes. Because what began as a question about a strange void in space now turns into a more difficult question about the observer who found it. Because once the observer enters the mechanism, the argument stops being merely astronomical. It becomes epistemological in the most unforgiving way. Not the soft seminar room version of that word. Something harder, something physical. A question about what kind of knowledge is even possible when every measurement of the whole must be taken from inside one unchosen part of it. That is the hidden pressure beneath the local void idea. It is not only trying to explain why one number came out too high, it is exposing a vulnerability in how cosmology imagines its own point of view. The discipline depends, at a deep level, on the conviction that by averaging over enough distance, correcting for enough local motion, and building models powerful enough to absorb the universe's messiness, the observer can eventually disappear into statistical neutrality. The local patch becomes a nuisance, then a correction, then an irrelevance. At least that is the hope. But the void reopens the question. What if the observer does not disappear that easily? What if here is still in the data long after we thought it had been averaged away? That is why the Hubble tension began to feel larger than the number itself. A mismatch of a few kilometers per second per megaparsec does not sound like a metaphysical wound. But if that mismatch survives because our local cosmic environment has leaked into one of the cleanest measurements in astronomy, then the problem is no longer numeric, it is structural. It means the route from observation to cosmology is more contaminated by location than the rhetoric of universality tends to admit. And that, more than the void itself, is what makes the story difficult to live with. Because physics is comfortable with mystery when the mystery sits far away, in a black hole interior. in the first fraction of a second after the Big Bang, in regimes of energy we cannot reach. But this is a different kind of discomfort. It says the source of uncertainty may not be hidden in some remote frontier. It may be braided into the ordinary sky around us, into the galaxy counts we built our maps from, into the local recession field we treated as background, into the fact that our species happen to emerge in one particular fold of the cosmic web and then try to infer the whole from that fold outward. A biased answer is unsettling. A biased vantage point is worse. Because you can correct an answer once you know it is wrong, a vantage point follows you into every correction you make. It shapes what even counts as normal. It decides which departures from theory look dramatic and which look ignorable. It influences what baseline you trust before you have reason to distrust it. If our neighborhood is underdense enough to matter, then the local universe has not merely tilted one parameter. It may have quietly educated us into the wrong intuition about how quickly local irregularity fades into cosmological truth. That is a much deeper problem than a single bad number. It is the problem of hidden innocence. Science advances by eliminating false privileges. We learned not to treat Earth as central, not to treat the Sun as singular, not to treat our galaxy as the frame around which the universe organizes itself. But there is a subtler privilege we may still cling to. The privilege of assuming our observational environment becomes neutral quickly enough to trust the transition from local measurement to universal claim. The local void scenario does not accuse us of vanity. It accuses us of convenience. We wanted here to become irrelevant on schedule. Reality never signed that agreement. This is where the Hubble tension acquires its most dangerous possibility. Not that one side has overlooked an error, not even that the standard model will need revision. Something stranger than both, that the nearby universe measurement and the early universe inference may each be faithfully reporting truths rooted in different effective conditions. One truth from a universe before large-scale local structure matured into a serious contaminant. Another from a universe viewed through the mature terrain of that structure. Neither fraudulent, neither careless, just not cleanly interchangeable. The dangerous possibility is that both sides are right. Right in different senses, right at different scales, right under different observational burdens. That is a much more treacherous situation than an ordinary disagreement. A disagreement invites adjudication, better data, better calibration, better theory. One side eventually wins. But when two measurements are each tethered to a different slice of cosmic reality, the conflict becomes harder to resolve because the language of the answer itself begins to fray. We speak as though there should be one number waiting untouched behind all methods. And there is, in the deepest theoretical sense. But, observationally, the path to that number may run through structures that imprint part of themselves onto the inference. A single constant approached through unequal worlds. That is what makes the Hubble tension so psychologically potent. It is not just that the universe seems to be saying two things at once. It is that both statements may be lawful consequences of how and when we ask. One emerges from the infant universe, where the matter distribution was still close enough to smoothness that our present local peculiarities had not yet become a serious epistemic burden. The other emerges from the late universe, after gravity has had billions of years to deepen wells, drain voids, and build the environment through which all nearby observations now pass. And once you see the problem that way, the void changes status. It is no longer merely a candidate explanation. It becomes a diagnostic instrument. Even if it fails as a complete solution to the Hubble tension, it still teaches something profound. It teaches that the observer's environment is not guaranteed to be a negligible detail. It teaches that a local structure can remain observationally relevant at scales where intuition had already declared neutrality. It teaches that late-time universe is not one smooth arena, but a deeply textured field in which position still matters after the equations have begun to idealize it away. That alone would be enough to force a rewrite of the emotional story cosmology tells about itself. For a long time, the great elegance of the field came from its ability to transcend the local, start with one sky, one species, one planet, one galactic location, and through measurement and theory, recover truths about the cosmos as a whole, It is an extraordinary achievement. It remains one. But the local void argument reveals that transcendence is not a completed state. It is a negotiated one, hard won, approximate, vulnerable to revision. The observer can be statistically humbled and still remain physically inconvenient. That distinction matters because it preserves rigor without surrendering to nihilism. The point is not that cosmology is impossible. The point is not that everything is local. The point is not that the universe refuses to be known. The point is sharper than that. Knowledge of the whole must pass through the grain of the part. And the grain may be coarser than we hoped. This is the second ignition in the story. The first was realizing that a vast underdensity may surround us and bias local motion. The second is realizing that this does not merely alter one measurement. It reclassifies the observer, no longer an external reader of cosmic truth, corrected only for small nuisances, but a participant in a structured environment whose density profile can feed directly into the interpretation of universal law. That is not mysticism. It is the plain consequence of doing cosmology from inside a lumpy universe. And once the observer has been exposed this way, a deeper question begins to press forward. How much of modern cosmology depends, not just mathematically, but emotionally, on the assumption that we are typical enough for local bias to remain safely beneath the threshold of consequence? How much of our confidence rests on the belief that the sky around us becomes representative fast enough, smoothly enough, honestly enough, that the grand claims can begin before the local terrain has fully ceased to matter? Maybe that belief is broadly justified. In many contexts, it is. But broadly justified is not the same as harmless in precision work. A large local underdensity does not need to overthrow the cosmological principle to expose its practical fragility. It only needs to show that the route by which real observers access universal claims is less pristine than the final equations suggest. That is why the local void story is so much more than a niche dispute about structure formation. It is a test of whether cosmology can admit that perspective still bites. Not in the old, flattering way. Not because we are central, because we are situated. And situated observers carry a burden that central observers never did. A central observer thinks the universe organizes itself around him. A situated observer knows the universe does no such thing, yet still has to reckon with the fact that his location may bias what can be inferred from the light that reaches him. That is a more mature humiliation, more scientific, less dramatic on the surface, but ultimately more destabilizing because it leaves the observer neither privileged nor irrelevant, just embedded. And embeddedness is harder to correct for than ego. Ego can be renounced in a sentence. Embeddedness has to be modeled, measured, and carried through every inference. It cannot be solved by intellectual modesty alone. It requires structure, dynamics, surveys, simulations, velocity fields. It demands that philosophy cash out in data, which is exactly why the next step in the story has to move out of rhetoric and into the harsher machinery of the standard model itself. Because once you accept that a local underdensity could matter, you are forced into a harder question. Can a universe like ours actually produce something like this without breaking its own rules? Can ordinary structure formation generate a deficit large enough, coherent enough, and extended enough to bias the nearby expansion rate in a meaningful way? That is where sympathy for the idea stops being enough. Now the model has to answer for the terrain, because that is where the argument becomes dangerous in a new way. Up to this point, the local void idea can still live on conceptual force. The mechanism is real. The observational vulnerability is real. The epistemic discomfort is real. But none of that is enough. Cosmology is not persuaded by unease. It has to ask the harder question. Can the standard universe we already believe in actually produce a structure like this? Not in the poetic sense, not in the sense that voids exist in general. They do. The late-time universe is full of them. Gravity amplifies initial irregularities. Dense regions grow denser. Underdense regions lose matter and expand relative to the background. The cosmic web emerges precisely because matter did not remain smooth. Filaments sharpen, clusters thicken, empty regions widen. In that broad sense, there is nothing exotic about a void. a universe governed by ordinary gravity, cold, dark matter, and expanding spacetime should make them. The real issue is scale. A small or moderate underdensity is not enough. The local environment has to be wide enough, deep enough, and coherent enough to leave a measurable imprint on the relation between nearby distance and recession. That means the debate is no longer about whether voids exist. It is about whether one of the more awkward versions of them, an unusually extended local deficit surrounding our observational position, is statistically plausible inside the standard model, or whether invoking such a thing quietly smuggles in a structure the model does not comfortably generate. That is where simulations enter the story, and simulations are merciless. They are where cosmology stops speaking in intuition and starts asking the universe to build itself under specified rules, seed the early fluctuations, let gravity evolve them, let dark matter collapse, let baryons follow, cool, ignite, complicate everything. Then look at the resulting distribution of structure and ask, how often do regions resembling our suspected local underdensity actually appear? This sounds cleaner than it is. Simulations are powerful, but they do not hand out simple verdicts. Everything depends on volume, resolution, assumptions, selection criteria, how the void is defined, what density contrast counts as significant, what radial profile you accept as similar, and where you draw the line between a rare tale of ordinary structure and something awkward enough to strain the model that produced it. That last distinction is the one that matters, because the standard cosmological model does not have to make our local environment likely. It only has to make it possible often enough that our situation does not look like a quiet indictment of the framework itself. Rare is acceptable, impossible is not. The trouble is that the most interesting structures usually live in the unstable territory between those two words, unlikely enough to worry you, plausible enough to survive. The local underdensity appears to live there. Some analyses argue that something like the KBC profile can arise within ordinary structure formation, especially once one allows for the messiness of real environments, the ambiguity of void boundaries, and the fact that observers do not get to choose especially clean positions from which to diagnose their surroundings. In that view, the local deficit is not a rebellion against the standard model. It is an uncommon but lawful expression of it, a tail event, perhaps, but still part of the distribution. If so, then the Hubble tension may be softened not by new physics but by a better appreciation of how late-time structure contaminates nearby inference. Other analyses are less forgiving. They argue that the required underdensity, if tuned to do enough work on the expansion discrepancy, becomes too large, too deep, too coherent, or too conveniently centered on us to sit comfortably inside the model's ordinary expectations. In that reading, the void may exist in some moderate form without doing nearly enough to resolve the tension, or it may ease part of the discrepancy while leaving the deeper split untouched. The structure then becomes important, but not decisive, a real environmental effect that still fails to carry the full explanatory burden placed on it. That ambiguity is not a weakness in the story. It is the story. Because this is what reality looks like near the edge of inference, one mechanism clearly real, one application plausibly important, one hoped-for resolution not yet securely earned. The public appetite is always for a clean ending. Either the void fixes the Hubble tension, or the void is irrelevant. Either the standard model survives untouched, or a giant hole around us exposes its failure. But precision cosmology almost never grants that kind of theatrical simplification. The truth is usually harder to metabolize. A structure can be real, important, and insufficient all at once. And insufficiency, in science, can still be transformative. Because once a local underdensity becomes large enough to matter even partially, the observer's environment can no longer be treated as a trivial nuisance. The standard model may survive. The early universe inference may survive. The distance ladder may survive. But the path connecting them becomes less innocent than it looked. Local terrain starts to act less like noise and more like an interpretive medium. That is already a severe outcome. One of the strangest habits in scientific storytelling is that only total overthrow gets treated as profound. If a model collapses, the narrative knows what to do, If everything remains intact, the narrative relaxes. But many of the deepest shifts in understanding happen in between, not when the law is destroyed, but when the conditions under which the law is accessed turn out to be more entangled than expected. A local underdensity does exactly that. It does not necessarily abolish the concept of a global expansion rate. It does not necessarily force a replacement of the standard cosmological model. It does something subtler and, in some ways, more destabilizing. It raises the cost of moving from local observation to universal statement. It says that the nearby sky may not be a transparent opening onto the whole, but a structured filter whose influence persists longer and farther than comfort would like. This is why simulations matter so much. Not because they deliver a simple yes or no, but because they force cosmology to confront the tale of its own distribution. A model is never judged only by its average outcomes. It is judged by whether the strange worlds it permits are strange in the right way. If our local environment is one of those worlds, rare but allowed, then the Hubble tension becomes partly a story about bad cosmic luck. If it is too rare, too geometrically convenient, or too weakly produced to do the necessary work, then local structure remains relevant but not sufficient, and the burden shifts elsewhere. Either way, the innocence is gone. The observer has already been contaminated by context. This is why the local void discussion does not need to win in a total sense to change cosmology. Even a partial environmental contribution is enough to reopen deeper questions about sample variance, representativeness, and how quickly local deviations are assumed to wash out. That phrase, wash out, is more revealing than it first sounds. It implies a confidence that roughness fades into neutrality on schedule, but the universe is under no obligation to make that schedule convenient for us. A few 100 million light-years can still be local in the mathematical rhetoric of cosmology and yet be immense enough to matter for real-world inference. A finite observer lives and dies inside that gap. And so, the standard model faces a difficult sort of scrutiny here, not the spectacle of being contradicted outright, but the quieter embarrassment of being asked whether its own lawful structure formation may have built an observational trap around us. That is a more intimate test. It is not about whether the equations are false. It is about whether the equations, when allowed to generate a real universe, produce the kind of positional awkwardness that makes universal measurement less clean than theory alone would suggest. Sometimes the universe does not break. Our certainty does. That is the line running underneath the simulation debate. A structure large enough to influence the local expansion rate need not announce some exotic new force. It may simply reveal that the standard universe contains enough irregularity to make a locally measured global number more fragile than we hoped. Or, just as unsettling, it may reveal that the structure required to explain the whole tension is too extreme for standard formation to provide comfortably, leaving us in a worse position than before. One real local bias, one unresolved residual discrepancy, and no clean story capable of absorbing both. That second possibility is particularly severe, because then the Hubble tension does not reduce to a single culprit at all. It becomes layered, part environmental effect, part systematic uncertainty, part unresolved model strain, perhaps. The neat drama collapses into overlapping causes. And when that happens, the deepest threat is no longer dramatic new physics. It is misplaced confidence, the confidence that one crisp explanation should exist simply because the anomaly is famous enough to deserve one. Reality is not organized by narrative appetite. It may be that the local underdensity only eases the discrepancy. It may be that it sharpens our understanding of where the distance ladder is vulnerable without actually rescuing the standard model from deeper pressure. It may be that it survives as a real but incomplete component of the puzzle. But even in that modest outcome, something profound has already happened. Cosmology has been forced to admit that where we are is not a philosophical footnote. It is part of the machinery. And once location becomes machinery, another layer of discomfort begins to surface, one that is harder to formalize and therefore easier to underestimate. Because if our position can bias a universal measurement, then the issue is no longer only one of structure formation or parameter inference. It becomes a question about typicality itself, not whether we are special in some mystical sense. Whether we are typical enough to trust how quickly we stop asking that question. That is where the discomfort stops being merely technical and becomes almost philosophical by necessity. Not because cosmology has drifted into abstraction, but because any science that tries to infer the whole from one embedded vantage point eventually runs into a question it cannot permanently postpone. How typical is the place from which the inference begins? For a long time, that question was kept at a safe distance by a healthy instinct. We are not central. We are not chosen. The universe does not arrange itself around human convenience. Those corrections were necessary. They remain necessary. But there is a quieter assumption hidden inside them, one so reasonable that it often goes unspoken. Even if we are not special, we are probably ordinary enough, quickly enough, that local irregularities can be treated as passing contamination rather than deep structural risk. The local void problem presses directly against that assumption. Not by proposing that we inhabit some miraculous center, not by reviving old fantasies of cosmic favoritism, by asking something far more disciplined. What if we are not special and still not representative enough for precision measurement? That is a harder thought to metabolize because it offers no consolation. A central position flatters. An unrepresentative one merely inconveniences. It gives us no cosmic dignity, only extra error bars. No throne, just a skewed floor. And yet science has to be able to think this way, because typical is not a metaphysical compliment. It is a statistical claim. It is about where an observer is likely to emerge, what kind of region that observer is likely to occupy, and how much that region is allowed to bias what the observer can infer. Those questions become unavoidable the moment local structure starts contaminating a supposedly universal quantity. This is why observer position is not a philosophical footnote to the void story. It is one of its hidden payloads. If the nearby universe around us is significantly underdense, then our location is not merely one more local detail to be cleaned away with routine correction. It becomes evidence that the path from local measurement to global truth depends on an assumption of representativeness that may be more fragile than the rhetoric of cosmology usually admits. The observer is not simply somewhere. The observer is somewhere that may matter. And once somewhere matters, the language of typicality can no longer be avoided. The temptation here is to run too far and too fast. To slide from our position may bias this inference into full-blown anthropic theater, as if the universe has somehow arranged conditions around us on purpose, or as if every anomaly must be translated into a sweeping statement about why conscious beings can only appear in certain strange cosmic environments. That is precisely the kind of inflation the subject does not need. The disciplined version is already strong enough. No purpose is required. No cosmic intention is required. Not even strong anthropic reasoning is required. Only the recognition that observers are physical systems arising in particular environments, and those environments may not be observationally neutral. That sounds almost trivial when phrased calmly. It is anything but trivial in practice, because the entire ambition of observational cosmology is to take the contingent conditions of one location and climb from them toward claims that hold everywhere. If location enters the inference more deeply than expected, then cosmology does not collapse, but it becomes more expensive. Every step upward carries the burden of proving that the local environment has truly stopped mattering. And proving a negative like that is notoriously hard, especially when the sky never announces its biases in plain language. Think about the asymmetry this creates. If we lived in an extraordinarily dense region, the sky around us might have felt busy, gravitationally heavy, perhaps obviously strange in some intuitively satisfying way. But a large underdensity is different. It can host ordinary astronomy, ordinary galaxies, ordinary night skies, ordinary local life. It does not scream bias. It whispers through counts, motions, deficits, and gradients that only emerge statistically, which means a non-typical environment can still feel normal from within. That may be the most treacherous thing about all this. The observer does not experience representativeness directly. The observer experiences familiarity. And familiarity is a terrible guide to cosmology. We call our region normal because it is what we learned the universe from. We built our intuition from the sky we actually have, the recession patterns we can actually measure, the large-scale maps our vantage point allows us to construct. If that region is underdense, then the resulting intuition does not come with a warning label. It becomes the background against which all later surprises are judged. A biased environment can teach you the wrong idea of ordinary. That sentence reaches beyond the void itself. It cuts toward one of the deepest difficulties in any embedded science. We do not discover the whole from neutral ground and then compare our position against it. We discover the whole by extrapolating outward from wherever we are, which means the baseline is local before it becomes universal. If the baseline is skewed, then the skew does not merely affect one result, it infects expectations. This is what makes the idea of observer typicality so hard to handle responsibly. Treated carelessly, it devolves into metaphysical fog. Treated correctly, it becomes a sober recognition that observational context matters more than pride allows. The question is not, are we special? That question is almost always too crude to be useful. The better question is, how much local deviation can a universal inference tolerate before confidence becomes overconfidence? The void sharpens that question with unusual force. Because the Hubble tension is not some obscure parameter dispute buried in the weeds of astronomy, it touches age, distance, structure growth, model consistency, and the bridge between the early and late universe. If a local underdensity contributes even part of the discrepancy, then our observational environment has already entered one of the field's most important numbers. That alone is enough to force a reappraisal of how casually we use words like representative, average, or typical, when the measurements become precise enough to punish every hidden convenience. And there is a larger irony here. The cosmological principle, the idea that the universe is homogeneous and isotropic on large enough scales, was partly meant to free us from exactly this anxiety. It says that no place, when averaged broadly enough, should be privileged. In the grand statistical sense, that remains one of the best supported and most fruitful assumptions in all of cosmology. But statistical homogeneity is not the same thing as observational innocence. It is a statement about the large-scale ensemble. We do not live in the ensemble. We live in one realization. One draw, one patch, one particular route through the cosmic web. And a single realization can be lawful while still being awkward. That is the mature form of the problem. We are not asking whether the universe has violated its large-scale order. We are asking whether one lawful realization of that order can leave an observer in an environment biased enough to contaminate a precision measurement. That is a very different claim, and a much more plausible one. It does not threaten the broad architecture of cosmology. It threatens the smoothness of the ladder by which we reach it. Which is why the local void story keeps deepening every time it seems ready to settle. First, it is about missing matter, then about altered motion, then about a biased expansion rate, then about the observer's role in the machinery, and now, beneath all of that, about whether a science of the whole can ever completely escape the fact that it begins in one unchosen place. There is no melodrama required to make that profound. It is already profound enough. Because once you accept that observer position may matter at this level, another thought follows with almost mechanical force. The local universe around us is not only structured in space, it is structured in time. We do not just inhabit one place in the cosmic web, we inhabit one era in cosmic history, a specific stage at which voids have matured, galaxies still shine, and distant evidence remains visible enough to reconstruct the whole. That means typicality has a temporal side as well. Not just where we are, when we are, and once that realization begins to move, the void changes again. It is no longer only a story about an underdensity around us. It becomes part of a larger and more haunting possibility. That cosmology itself is being practiced during a narrow window in which the universe is still legible, and that both our place and our epoch may be more entangled with what we can know than the clean language of universal law usually lets us feel. The structure around us may bias the measurement. The age we live in may be the only reason the measurement is still possible at all. And that means the final part of this descent cannot remain inside the local neighborhood. It has to widen, from our void to the era that lets us see it. because the era matters almost as much as the location. It is easy to forget that when speaking about cosmology, because the language of the field is so often framed in permanent terms. The age of the universe, the expansion rate, dark energy, matter density. Parameters sound like fixed features of a finished machine, as though the cosmos had already settled into its final readable form, and all we have left to do is improve our instrumentation. But the universe is not a finished machine. It is a process caught in motion, and the fact that we can still see enough of that process to reconstruct it may be one of the least appreciated contingencies in the whole human attempt to understand reality. We do not merely live somewhere. We live sometime. That matters because the sky is historical. Every measurement in cosmology is a measurement of timing disguised as light. We see galaxies not as they are, but as they were when their light left them. We infer expansion by comparing epochs embedded in that light. We reconstruct the early universe through radiation released nearly 14 billion years ago, and then stretched across space by the same expansion we are trying to quantify. We treat the visible sky as evidence because the universe still preserves enough contrast, enough memory, enough accessible structure for the evidence to remain legible. That condition will not last forever. This is one of the coldest facts in modern cosmology, and one of the most beautiful in a severe way. The universe is not merely expanding, its expansion is accelerating. On the largest scales, distant galaxies are not only receding, many are being carried away into a future in which their light will eventually redshift beyond practical detectability. The cosmic microwave background itself will continue to cool and stretch, becoming weaker, longer, harder to distinguish against noise. The great large-scale evidence that lets a civilization infer the Big Bang, cosmic expansion, and the architecture of the cosmos is not permanent scenery. It is time-sensitive data. We happen to exist during an epoch when the sky is still explanatory. That is a staggering thing to say plainly, not because it implies destiny, it does not. Not because it makes humanity cosmically important, it does not. But because it reveals that cosmology is being practiced inside a narrow window between two kinds of blindness. The blindness of the early universe, before complexity could arise to ask questions, and the blindness of the far future, when enough evidence will have faded beyond the observable horizon that many of our deepest present conclusions may become inaccessible from within ordinary late-time observation. In the distant future, a civilization living in a galaxy like ours may see only its own bound structure surrounded by apparent darkness. The broader expansion could be invisible to them. The microwave background could be diluted beyond recovery. The relic signatures of a hotter, denser beginning could disappear beneath thresholds of detectability. The great historical scaffolding on which modern cosmology rests might no longer be readable from inside the cosmic island that remains. The map is not only incomplete, it is fading while we read it. That fact changes the tone of everything that came before. The local underdensity around us, if it is real in the relevant sense, teaches one lesson about situatedness. Where we are can bias the answer. The temporal condition of cosmology teaches another. When we are determines whether the question can even be asked with success. Space and time are both entering the inference. Our patch of the cosmic web may be observationally awkward. Our epoch may be observationally privileged in a way that is not flattering, only finite. And together they create a deeper unease. Because once you see cosmology this way, the dream of a view from nowhere begins to recede, not collapse, recede. The laws remain lawful. The equations remain powerful. The large-scale model remains one of the greatest achievements of human thought. But the path by which finite beings reach those laws begins to look less like a clean ascent and more like a narrow corridor opening briefly through circumstance. A corridor through one region of structure, in one era of cosmic visibility, under one set of local conditions that history happened to produce. That does not make the knowledge unreal. It makes it fragile. And fragility changes the emotional texture of understanding. We often imagine scientific progress as something that simply accumulates, each generation adding another brick to a permanent structure. But cosmology has always been stranger than that. It is an attempt to infer the whole from a limited observational shell, and that shell is itself evolving. Some truths become accessible only after enough structure forms. Others become inaccessible once expansion carries too much evidence away. The universe does not offer itself to observation all at once. It opens and closes channels of legibility across time. We are standing inside one of those channels. That realization should make the local void story feel larger, not smaller, because now the issue is no longer just whether our immediate environment can bias a precise measurement. It is whether cosmology as a whole is conducted under a double contingency, a specific place in the large-scale structure, and a specific epoch in the history of observability. The void around us, if present, is a local expression of that contingency. The accelerating universe is the temporal one. Together they say something harsher than wonder usually admits. Reality may be lawful without ever being comfortably available. That is the mature form of the unease. The universe does not have to hide its laws to make them difficult to know. It only has to make access to them, dependent on conditions that are partial, local, and impermanent. A local underdensity can tilt one of our key measurements. A late-time observational window can make the broader architecture of the cosmos visible for a while and then quietly close. Neither of those facts invalidates cosmology, but both destroy a certain innocence about it. They reveal that universal knowledge is not merely a matter of intelligence and technique, it is also a matter of circumstance. And circumstance has texture. We emerged after stars had forged heavy elements, after galaxies had matured enough to host planets and chemistry, after structure had become rich enough to give the sky depth, but before cosmic acceleration had erased too much of the evidence. That sequence is not mystical, it is physical, yet the physicalness of it is exactly what makes it so severe. We do not get to know the universe under arbitrary conditions. We get to know it under the conditions that happen to produce knowers, with whatever local biases and temporal opportunities those conditions carry. This is why the local void hypothesis, even in its most modest form, reaches beyond itself. If it merely softened the Hubble tension a little, it would still matter, because it would have exposed the practical cost of being embedded. It would have shown that not only are we late-time observers in a structured universe, but our specific structure may be one of the things shaping the answer we take to be cosmological. It would mean that our most foundational numbers are not extracted from a neutral stage, but from a stage still built out of historical accidents the universe never promised to average away on human timescales. Human timescales. Even that phrase is too small. On cosmological scales, the entire era in which expansion, relic radiation, galaxy surveys, and large-scale structure can all be cross-read into one coherent story may be brief, vast in ordinary imagination. Brief in cosmic terms. A narrow interval in which the universe is not just there, but decipherable in the particular way modern cosmology requires. And we are inside it. That sentence can be misused if handled cheaply. It can be inflated into false profundity, into the sort of empty cosmic awe that says everything and means nothing. So, it has to be kept under discipline. The point is not that our era is sacred. The point is that observability has a history. The evidence we rely on is not eternally available. The sky itself has conditions of readability. That is a physical statement, not a poetic one. Once you hold on to that, the local underdensity around us begins to feel like part of a larger architecture of limitation. We are not merely creatures trying to understand a vast universe. We are creatures trying to understand it from inside one structure, during one observational phase, using light that arrives already filtered by both. The aspiration of cosmology is universal. The route to it is irreducibly situated. This is the point where a weaker script would start summarizing. It would widen into abstract reflection and lose the concrete pressure of the original problem. But the pressure here should sharpen, not soften. Because everything we have uncovered, the local deficit, the altered motion field, the split between early and late measurements, the contamination of the observer, the fragility of typicality, the temporariness of cosmic legibility, has been converging on one conclusion. The universe is not broken. The clean observer is. Not morally, not intellectually, structurally. There is no place outside the cosmic web from which to measure the web without inheritance. No era outside cosmic history from which to read that history without loss. We are not detached auditors of the universe. We are products of one part of it, measuring the rest through the residue of where and when we formed. That does not make our knowledge false. It makes it conditional in a way that universal laws themselves are not. And once you feel that distinction, the original question returns in a different form. Not simply how fast the universe is expanding, but what it means to claim that answer from here, now, inside this particular fold of matter, during this particular interval of visibility, before the evidence thins and after structure has already scarred the sky with its own local biases. That is the older, larger, more adult version of the problem. And it leaves us with one final task: to return to the number where this began and ask what, exactly, it has been measuring all along. All along, it was never measuring expansion in isolation. That was the convenient fiction, useful, elegant, often close enough to true that it could do real work. But no astronomer has ever touched the expansion of the universe directly, as if it were a bare quantity laid out in clean air. What we actually measure are signals, light curves, redshifts, brightnesses, distances, motions, arriving through a structured cosmos and interpreted by models that try, with increasing sophistication, to separate the global from the local, the universal from the environmental, the law from the terrain through which the law is glimpsed. The number at the center of this story was never just a number. It was an argument about what can be safely ignored. That is why the Hubble tension refuses to behave like an ordinary mismatch. If it were only about calibration, the emotional structure of the problem would be smaller, annoying, but familiar. If it were only about spectacular new physics, the emotional structure would be cleaner, dramatic, but recognizable. Instead, it sits in a harsher place, where the universe may be lawful, the measurements may be serious, and the remaining conflict may still reveal that our hidden assumptions about neutrality were too generous. That is the deeper threat. Not that cosmology made a foolish mistake, that it made an elegant one. Elegant mistakes are the hardest to notice because they fit so well inside the architecture of success. They do not arrive as embarrassments. They arrive as simplifications that work beautifully until precision becomes sharp enough to reveal the cost of what was simplified away. The assumption that local structure fades into irrelevance fast enough for nearby measurements to become representative was never absurd. It was one of the practical terms on which cosmology became possible. But practical terms are not eternal truths. They are bargains with the scale of the problem. And once the problem becomes precise enough, old bargains start to fail. This is where the local void ceases to be merely one explanatory option among others and becomes something more lasting, a test of intellectual discipline. Can we admit that an environmental effect is important without demanding that it solve everything? Can we distinguish a real bias from a total explanation? Can we let a structure be consequential without turning it into mythology? Those questions matter because science is often at its most vulnerable not when it faces ignorance, but when it faces partial knowledge. A full mystery is easy to name. A full solution is easy to celebrate. A partial correction that changes the shape of a problem without ending it is much harder to live with. It denies the comfort of climax. It leaves us with a world that is more entangled, more conditional, and less narratively obedient than we wanted. A local underdensity may be exactly that kind of correction. Perhaps it softens the Hubble tension, but does not erase it. Perhaps it explains part of the excess in the local expansion rate while leaving some deeper discrepancy untouched. Perhaps it sharpens our understanding of how late-time structure contaminates nearby measurements, without absolving cosmology of every other unresolved pressure. If so, that is not a failed idea. It is a serious one. Because a partial truth that exposes hidden dependence is often more valuable than a total explanation bought too cheaply. And dependence is the real subject now. Not just the dependence of one measurement on one structure, but the dependence of cosmological confidence on assumptions that only reveal themselves once the numbers become fine enough. Once you are comparing percent-level discrepancies in a universe this large, every quiet simplification becomes dangerous. Representativeness, sample variance, velocity corrections, distance calibration, model priors. None of them are decorative anymore. They are not side notes to the real cosmology. They are the route by which real cosmology is permitted to exist. That may be the most important thing the void teaches, even if the void does not carry the whole burden of explanation. There is no clean border where interpretation begins after environment ends. There is only the labor of disentangling them. And disentangling them is harder than people outside the field tend to realize, because modern cosmology is not one measurement repeated many times. It is a layered inference machine. One rung calibrates the next. One epoch constrains another. One model translates ancient structure into present parameters. One sky survey becomes the background condition for a later velocity correction. Everything leans, everything inherits. That is how precision is built, but it is also how local assumptions propagate farther than intuition expects. A sufficiently large underdensity exploits exactly that architecture, not because it breaks the machine, but because it enters through the seams of ordinary practice. It alters galaxy counts. It alters local flow fields. It alters what counts as a fair approximation to smooth expansion in the nearby universe. It alters, therefore, the burden placed on every correction intended to remove those effects. And by the time those altered conditions rise through the ladder into a final inferred value, the result can look universal while still carrying the imprint of where it was extracted. That is a hauntingly modern kind of error. Not a false reading, a contaminated one. And contamination is more difficult to cure than falsity, because it allows almost everything to remain competent. The telescope works. The calibration works. The model works within its stated limits. The statistical treatment is serious. The inference is reproducible. Yet a local asymmetry can still survive the entire chain, because the chain itself was never operating outside the universe's structure. It was embedded in it from the beginning. Which brings us back to the sharpest line in the entire story. Sometimes the universe does not break. Our certainty does. That line has to be handled carefully, because it can slip too easily into generalized relativism if left uncontrolled. But this story does not justify relativism. The laws do not become optional because observers are embedded. The cosmic microwave background does not dissolve into opinion. Galaxy surveys do not become literature. The point is narrower and more severe. Objective knowledge remains possible, but the path to it is more conditional, more situated, and more vulnerable to hidden structure than the polished final form of theory tends to make emotionally visible. In that sense, the void is almost pedagogical. It forces cosmology to remember the difference between a law and the circumstances under which the law is inferred. Expansion itself is one thing. Our measurement of it is another. The same is true, in different ways, across all of science. But cosmology suffers the distinction with unusual intensity because it studies the whole from inside one part. There is no laboratory external to the universe, no control sample detached from cosmic history, no second cosmos against which to compare our own. There is only this one realization, this one position, this one era, and the attempt to extract from them statements that remain true beyond them. That attempt is heroic. It is also fragile. And fragility is not a flaw in cosmology. It is the condition under which cosmology becomes magnificent at all. A species on one small planet, in one galaxy, inside one structured region of a dynamic universe, trying to infer the global architecture of reality from relic light and recession patterns and statistical shortages and galaxy counts. That is an almost impossible ambition. The wonder is not that it encounters subtle traps. The wonder is that it gets as far as it does. But once you say that honestly, another form of humility becomes necessary. Not the old humility of cosmic smallness. We already know we are small, something more adult than that. Methodological humility. The humility to admit that the route from local observation to universal claim is not guaranteed to become clean merely because the equations are elegant. The humility to accept that a structure can be real, biasing, and incomplete all at once. The humility to let an anomaly remain layered when narrative appetite demands a single villain. The humility to distinguish between the universe being stranger than expected and our position in it being worse than expected. That last distinction matters more than it first appears, because the most seductive explanation for every cosmological tension is always new physics, something dramatic, something fundamental, something worthy of the scale of the field. But there is another possibility, one less glamorous and, in some ways, more sobering. The universe may already be lawful enough. The difficult may lie in how awkwardly we are placed to know that law with precision. A bad address can imitate a broken theory. That is what the local void threatens to prove. Not that the standard model must be abandoned, not that nearby measurements are useless, not that cosmology has failed. Only that confidence can become overconfident when the observer disappears too easily from the story. And once that realization matures, the ending is no longer about deciding whether the void wins. That is too crude a question. The more serious question is what remains true after the void has done its work on our intuition. What are we left with once the underdensity has stripped away the comforting fiction that measurement is cleanly separable from location? We are left with a universe whose laws may be universal, but whose accessibility is not. We are left with a cosmos that can be statistically smooth on vast scales and still observationally biased from within one lawful patch of structure. We are left with the possibility that one of the most famous tensions in modern science is not a signal that reality is inconsistent, but a sign that our local environment has not yet finished speaking inside our numbers. And we are left with something colder than surprise, a recognition that the universe may have been telling the truth all along. We were the ones hearing it from inside a gradient. From inside a gradient, even clarity arrives tilted. That is the final discipline this story demands. Not paranoia, not the collapse of confidence. Discipline, the ability to hold two truths at once without forcing them into a simpler drama than reality allows. The first truth is that the universe is astonishingly intelligible. We have extracted from faint light and distant motion a coherent account of cosmic expansion, primordial structure, galaxy formation, dark matter, relic radiation, and the broad thermal history of the cosmos. That achievement is not fragile in the shallow sense. It is not one loose claim waiting to be laughed out of existence by a single anomaly. The architecture is too deep for that, too cross-checked, too interlocked, too often vindicated by predictions made long before the relevant observations became possible. The second truth is that intelligibility is not the same thing as innocence. A theory can be powerful and still inherit hidden convenience from the conditions under which it is tested. A measurement can be excellent and still carry environmental contamination. A local truth can be honestly measured and still become misleading the moment it is mistaken for the whole. That is the colder lesson of the void. Not that knowledge fails, that access has texture. And texture is what smooth narratives erase first. This is why the deepest threat posed by the local underdensity is not really to the standard model as a list of parameters. It is to the psychological style with which cosmology often presents its parameters, as though each one emerged from the universe in a state of conceptual cleanliness, fully separable from the route by which it was inferred. The more precise the science becomes, the less that style can be trusted, because precision does not merely sharpen answers, it sharpens dependencies. It makes the hidden scaffolding visible. It reveals which assumptions were helping all along. A sufficiently large local underdensity does exactly that. It reveals that the number we thought was a direct statement about the cosmos may also be a statement about the cosmic terrain through which we asked. It turns one parameter into a mirror, not a mirror of human importance, but of human situation. That distinction matters enough to repeat in a different form. We are not important to the universe, but our position is important to the measurement. That is not vanity. It is geometry under gravity. It is what happens when finite observers try to read the behavior of a structured cosmos from inside one branch of its own development. The observer becomes relevant not because consciousness bends reality, but because location bends inference. And once that is visible, a great many older simplifications begin to feel slightly less safe. The language of late time versus early time cosmology becomes less like a convenient bookkeeping distinction and more like a warning that the universe before mature structure and the universe after mature structure are not observationally interchangeable. The idea of sample variance becomes less like technical caution and more like an admission that one realization of the cosmic web can remain inconveniently influential. Even the phrase local correction starts to sound overconfident because it assumes we already know the scale at which locality ceases to matter. Maybe we do, broadly speaking, but broad speaking is exactly what this anomaly no longer allows. And that is why the void remains dangerous even in partial victory. It does not need to explain the entire Hubble tension to permanently damage the old innocence. It only needs to prove that our local environment contributes in a serious way. Once it does that, the old story cannot fully return. Cosmology can no longer talk about the nearby universe as though it were simply the first rung of a neutral ladder. It becomes the first rung of a ladder standing on uneven ground. That image is useful because it preserves the right balance of force and restraint. An uneven ladder is not useless. It is dangerous to assume level. It can still reach something real. It can still be built with skill. It can still support ascent. But every later rung now depends on whether the tilt at the base was honestly understood. A small angle can propagate farther than intuition expects. The local void, in that sense, is not just one more structure in the cosmic web. It is a demonstration of propagation, of how a condition near the observer can travel upward through a measurement chain and emerge later as a tension in fundamental inference. It is an object lesson in how reality punishes conceptual laziness at high precision. And high precision is exactly where cosmology now lives. That is one reason this problem feels so modern. In an earlier era, the uncertainty would have swallowed it. The local environment would have been too poorly mapped, the distance ladders too noisy, the surveys too shallow, the model comparisons too coarse. The universe would have remained vague enough for innocence to survive. But modern cosmology has pushed itself into a different regime. Its measurements are now precise enough that the remaining errors are no longer allowed to be generic. They must have structure. They must have mechanism. They must have somewhere to hide. The void offers one such hiding place. Not as a conspiracy of missing matter, not as a secret chamber in the universe where the laws change. Something more ordinary than that, and therefore more unsettling. A lawful underdensity, produced by ordinary structure formation, sitting in the observational path of one of our most important measurements, quietly reminding us that the route from local sky to global truth was never a straight line. There is a temptation, at this point, to ask whether this makes cosmology tragic. That would be too theatrical. The field is not tragic in the sense of being doomed. Its corrections are real. Its methods improve. Its self-critique is one of the reasons it is so reliable. But there is a kind of severe beauty in watching a science become mature enough to discover the exact ways its own success was conditionally purchased. That is what this feels like. Not collapse, maturity. The kind that arrives when a discipline stops expecting the universe to be conceptually kind. Because conceptual kindness is what we were really relying on. Not just lawful behavior, but lawful behavior accessible through methods whose assumptions become harmless quickly enough. The local void story says, perhaps not. Perhaps the laws remain beautiful while the access route remains compromised. Perhaps the universe is under no obligation to let finite observers infer the whole without carrying the residue of where they stand. And if that is true, then the real achievement of cosmology is not that it found perfect neutrality. It is that it got this far without it. That thought changes the emotional balance of the whole story. The local underdensity no longer feels like a vandal threatening to ruin a clean picture. It feels more like an acid revealing hidden grain in a polished surface. The picture was never false. It was smoother than reality had earned. The void does not destroy the picture. It roughens it back toward truth. Which is why the next question cannot be, does the void win? That question belongs to narrative appetite, not intellectual seriousness. The better question is harsher and more durable. What survives once we stop pretending the observer is transparent? Some things survive easily. The universe expands. The early universe left relic radiation. Structure grew from primordial fluctuations. Gravity deepened density contrasts over billions of years. dark energy drives, late-time acceleration. None of that becomes optional because one local underdensity may bias part of one measurement chain. But some habits do not survive so well. The habit of speaking as though universal quantities arrive detached from the physical route by which they were inferred. The habit of treating local environment as technical clutter rather than a possible source of conceptual distortion. The habit of assuming representativeness before the sky has truly earned it. Those are the habits the void begins to strip away. And once they are stripped away, a final transformation occurs in the viewer's role as well. At the beginning of this story, the problem may have sounded like a distant feature of professional cosmology, an argument among astronomers about a disputed number and a giant thinning of matter somewhere around our galaxy. By now, that framing should feel too small, because what is really being exposed is not just a specialist debate, it is a universal condition of knowing from within. Every embedded intelligence wants the same thing, to separate reality from the angle from which reality is seen. Sometimes its separation works beautifully. Sometimes it fails only at the margins. Sometimes the margins turn out to include the very number you thought was safest. That is why the local void carries more force than its geometry alone would suggest. It is not just a region of lower density. It is a demonstration that emptiness can enter knowledge as bias, that absence can become mechanism, that what is missing around you can alter what seems true beyond you. And once you truly feel that, the story is no longer about emptiness at all. It is about inheritance. The measurements we make inherit the structure around us. The intuitions we trust inherit the sky we learned from. The questions we ask inherit the era that still allows them to be answered. We do not begin from nowhere. We begin from a world. And worlds leave fingerprints on every truth extracted from them. The final movement, then, is not to ask whether the universe has been broken by a void. It is to ask whether we were ever entitled to imagine that the universe could be measured from inside one of its folds without that fold speaking back. Without that fold speaking back, cosmology would have been easier, cleaner, at least more emotionally comfortable. The universe would still be vast, still cold, still almost absurdly beyond the scale of instinct, but the route from observation to truth would feel straighter. Measure enough objects, average over enough noise, correct enough local motion, and eventually the cosmos would surrender a neutral answer. That was always the hope beneath the mathematics, not just that laws exist, but that they become available to finite observers without too much residue from where those observers happen to stand. The void is what happens when that hope becomes too smooth to notice. Because a fold in the cosmic web does speak back, not in language, in gradients, in altered galaxy counts, in velocity fields, in a local expansion pattern that may run slightly ahead of the deeper background, in the quiet statistical insult of discovering that our neighborhood might be large enough to contaminate a universal claim. The underdensity around us, if it is real in the relevant sense, is not dramatic because it is empty. It is dramatic because it is enough. Enough less matter, enough less inward pull, enough environmental bias to matter, enough structure to remind us that the observer never vanished from the apparatus as completely as we imagined. That is the mature form of the whole argument. Not that local structure exists, that was always known. Not even that local structure can influence motion, that follows from ordinary gravity. The sharper point is that our specific fold of structure may be wide and coherent enough that one of the cleanest looking measurements in cosmology still carries its imprint. That is what reclassifies the issue from nuisance to wound. And once you see it that way, a strange reversal occurs. The void stops being the anomaly. The assumption of transparent observation becomes the anomaly. That is the real inversion at the center of this story. We began with a giant underdensity that sounded unusual, improbable, perhaps even narratively convenient. But the deeper we go, the less unusual it feels that structure should bias measurement. The more unusual thing is how long we were able to speak, as though universal inference could proceed with the observer reduced to a near-invisible correction. Not because cosmologists were careless, because the approximation often works. But approximations become dangerous when their success hardens into intuition. What once served as a useful simplification begins to masquerade as a property of reality. And reality is usually less well-behaved than the simplification that first let us touch it. This is where a weaker narrative would start reaching for grand metaphysical statements about humanity, consciousness, or our place in the cosmos. That would be a mistake. The force of this story does not come from flattering the observer. It comes from removing the observer's last comfort. We are not central. We are not cosmically chosen. We are not the reason the universe is the way it is. But we are also not exempt from the local conditions under which we try to know it. That is the humbler and more difficult truth. We are not privileged. We are implicated. That word is heavier than it first appears. To be implicated is not to be guilty. It is to be entangled. Our measurements are implicated in our location. Our confidence is implicated in assumptions about representativeness. Our models are implicated in the finite route by which one realization of the universe is generalized into a statement about the whole. The local void does not accuse us of intellectual arrogance in the old sense. It accuses us of forgetting how much knowledge depends on the physical terms of access. Access is the real subject now. Because once the observer is recognized as embedded, every clean cosmological claim begins to reveal the infrastructure beneath it, not to discredit the claim, but to expose what had been carrying it: survey geometry, selection functions, flow corrections, calibration ladders, priors, model bridges between early and late epochs. The cosmological principle itself, not as dogma, but as a statistical aspiration that must be reached through one finite realization rather than assumed at the start. None of that is embarrassing. It is what serious science looks like when it stops pretending purity and starts accounting for the cost of inference. And the cost, in this case, may be larger than we liked. A local underdensity does not have to overthrow the broad order of the cosmos to matter profoundly. It only has to reveal that one universal-looking quantity may have been measured through a regional distortion. That possibility alone deepens every later question. If this parameter can inherit local geography, what other supposedly clean inferences depend more heavily than expected on the conditions under which the sky becomes visible to us? Where else have we been speaking as though the observer were transparent when the observer was merely well-corrected? Those are dangerous questions. Not because they unravel everything, but because they cannot be limited cleanly once they are asked. They turn cosmology from a science merely of what the universe is into a science also of how the universe becomes knowable from within itself. That second science was always there, hidden inside the first. The void simply forces it into view. And once it is in view, the emotional register changes again. At the beginning, this was a story about a giant cosmic hollow, about missing matter on impossible scales, about a puzzle in the expansion rate. By now it should feel like something colder and more intimate, a story about how reality can remain lawful while making lawful knowledge conditionally accessible. The observer does not fail because the laws are obscure. The observer struggles because laws must be reached through structure, and structure leaves fingerprints on the reaching. That is why this idea feels so haunting. Not because it offers a spectacular alternative universe, because it offers this one only rougher, less conceptually kind, less willing to let us separate truth from position as easily as we hoped. A universe where the local sky can be good enough to build cosmology and still biased enough to deform one of cosmology's most important numbers. A universe where the broad model survives, but the route by which it is trusted becomes more conditional. A universe where the laws are universal and the access route is not. In some ways, that is more destabilizing than a dramatic breakdown. A dramatic breakdown gives you an obvious destination: new theory, new particles, new fields, new terms in the equations. But a positional wound is harder to metabolize. It does not tell you the universe is stranger in the grand sense. It tells you the observer is less cleanly situated than the grand story required. That is not the kind of revelation you solve by adding one term to a Lagrangian. It has to be carried through practice, through humility, through every future claim about what has truly been averaged away and what has merely been assumed to be. That is why the local void matters, even if its strongest advocates overreach, even if its exact profile shifts under better data, even if it ultimately explains only part of the discrepancy that made it famous. Its enduring contribution would remain the same. It would have forced cosmology to see that a lawful patch of structure can behave like a local, epistemic trap. Not because the patch is supernatural, because it is enough of the wrong kind of normal. That phrase matters too. The wrong kind of normal. A region that looks cosmically ordinary to the beings inside it. A region capable of stars, planets, galaxies, chemistry, and all the rest. A region not bizarre enough to advertise itself as an outlier, and yet still unrepresentative enough, at the relevant scale, to bias a measurement whose rhetoric had already become universal. That is exactly the kind of trap a mature universe would set. Not a theatrical one, a subtle one, a trap built out of lawful gradients, finite surveys, inherited assumptions, and the human tendency to stop questioning the background once the foreground starts yielding beautiful results. But the background was always part of the machinery. And once you admit that, something clarifies with almost brutal simplicity. The clean observer was never a physical object. It was an idealization, useful, often necessary, sometimes extraordinarily effective, but still an idealization. There is no actual civilization measuring the universe from nowhere. There are only situated observers, arising in specific structures, during specific epochs, trying to correct their way toward universality without ever escaping the history that produced them. We are one such observer. That is not a sentence about human destiny. It is a sentence about measurement. And measurement, at the highest level, is what this entire story has been about from the first line. Not emptiness as spectacle, not a void as a cosmic monster. Measurement. What it means to extract a number from a world that may already be leaning under your feet. What it means to speak about the universe as a whole while standing inside one fold of its own late-time architecture. What it means for precision itself to reveal that the route to truth was more local, more historical, and more conditional than the finished equations allowed us to feel. The void does not answer all of that, but it makes it impossible to ignore. And once it has done that, the final question is no longer whether our patch of the universe is strange. The final question is what exactly? We thought a universal measurement was supposed to look like when it came from a species that never had a neutral place to stand. A neutral place to stand was always the dream. Not because anyone literally believed such a place existed, but because the entire aspiration of cosmology leans toward it. Every correction for local motion, every larger survey volume, every refinement of the distance ladder, every appeal to statistical homogeneity is, in its own way, an attempt to approach a view from nowhere without ever being granted one. It is a discipline built on asymptotic humility, the hope that if we average carefully enough, model honestly enough, and distrust our conveniences deeply enough, the local will eventually loosen its grip and the universal will come through. Most of the time, that hope is justified enough to be magnificent. But this story has been about what happens when justified enough reaches its limit. Because a universal measurement does not arrive in the abstract, it arrives through a route, through one sky, one matter distribution, one epoch of observability, one inherited structure of motion and density, one history of calibration, built from objects close enough to us that our environment can still matter. The cleaner the final number looks, the easier it is to forget the root. The void is dangerous because it drags the root back into view. And once the root becomes visible, another realization hardens. The universe may not merely be difficult to understand. It may be easiest to misunderstand in the precise places where understanding first becomes possible. That is the severe beauty in all this. We emerge in a cosmos rich enough to generate galaxies, stars, chemistry, and minds. Rich enough. Also, to generate large-scale structure, underdensities, peculiar motions, and observational traps. The same universe that made cosmology possible also made it conditional. The same history that gave us the evidence gave the evidence texture. There was never any guarantee that the sky would be both legible and fair. Legible, perhaps fair, not necessarily. A local underdensity is unfair in exactly that sense. It does not make cosmology impossible. It makes the first clean answer harder to trust. It makes the observer work longer to prove that what looks universal has actually escaped the influence of nearby terrain. And terrain is the right word, because this is no longer just about one parameter or one anomaly. It is about the shape of the ground from which universal claims are launched. The ground may not be level. That line belongs at this point because it converts the whole story back into something almost bodily. For all the abstraction of cosmology, for all the equations, spectra, simulations, and parameter fits, the deepest unease here is simple enough to feel physically. Imagine trying to determine whether the horizon itself is tilted while standing on a slope too broad to notice directly. Your instruments are good, your method is careful, the stars are real, the horizon is real, but the unnoticed inclination beneath your feet enters the measurement before you ever name it. That is what the void threatens to be, a slope large enough to impersonate neutrality. And that is why the ending cannot be a conventional conclusion about whether the KBC void is definitely this or definitively that. Reality has not yet granted so cheap an ending. The observational profile remains debated. The statistical plausibility remains argued over. The extent to which a local underdensity can resolve, soften, or merely complicate the Hubble tension remains unsettled. To pretend otherwise would violate the discipline this story has been trying to earn. But uncertainty does not weaken the meaning here. It sharpens it. Because even in uncertainty, the lesson already stands. If our local environment contributes meaningfully to one of the central numbers in cosmology, then the problem was never simply, what is the expansion rate? The grown-up version of the question is more demanding. What part of the answer belongs to the universe? And what part belongs to the path by which the universe becomes observable from here? That is the matured form of the hook. It is where everything has been leading, the giant underdensity, the altered motion field, the split between local and early universe measurements, the failure of clean observer neutrality, the fragility of typicality, the narrowness of our observational epoch. None of these were isolated curiosities. They were all parts of one larger realization. Universal laws do not guarantee universal access. That is the cold architecture beneath the story. The cosmos may be governed by equations that hold everywhere, and finite beings may still encounter those equations only through conditions that are local, historical, and uneven. A law can be universal while its measurement is provincial. A truth can be global while its first appearance is distorted by one specific fold of matter. The void does not invent that condition. It reveals it. And once it is revealed, the emotional center of cosmology shifts very slightly, but permanently. Wonder no longer comes only from scale, from how large the universe is, how old it is, how strange its physics can become. Wonder begins to come from something sterner than that, the fact that knowledge itself has geography, that truth arrives through structure, that even emptiness can have consequences, that absence around the observer can enter the result as bias, that a civilization may come close to reading the universe correctly, while still hearing part of the answer through the echo of its own location. This is not pessimism. It is a more adult kind of awe. The childish version of cosmic awe says the universe is big and mysterious, and therefore overwhelming. The mature version says the universe is lawful, intelligible, and still under no obligation to make that intelligence easy for creatures inside it. The mature version is colder, better. It does not need exaggeration. It does not need fake profundity. It only needs the facts arranged honestly enough that their implication can be felt. And the implication here is difficult to escape. We may have spent years treating a local wound in the cosmic web as though it were a property of the entire cosmos. Or, just as unsettlingly, we may have discovered only part of that wound and still be underestimating how much our own surroundings have entered the answer. Either way, the old innocence is gone, the old fantasy that the observer disappears quickly, cleanly, almost automatically into the statistical smoothness of the universe. That fantasy does not survive this descent intact. What survives instead is more severe and more durable. The universe expands, structure forms, voids grow, observers arise inside one part of the structure, not outside it. They inherit a sky, they build a measurement, and then, if they are lucky and disciplined enough, they realize that the measurement has inherited them back. That is the line this entire script has been trying to reach. Because it resolves the opening without flattening it, The question was never just whether we live inside a giant void. The deeper question was what it would mean if we did. Not as spectacle, as epistemology made physical, as gravity entering knowledge through location, as local geography contaminating a supposedly universal number, as the realization that we do not merely observe the universe from somewhere, we observe it through somewhere. And through is heavier than from. To observe from somewhere is merely to have a position. To observe through somewhere is to have a filter. The local void, if it is real in the way that matters, is a filter made of missing matter. A filter made of less gravity, less inward pull, more outward drift, fewer galaxies than expected, and all the inferential consequences those deficits accumulate over cosmic time. A filter that does not darken the view, but tilts it. A filter subtle enough that life can flourish inside it, and astronomy can seem ordinary, yet consequential enough that one of our most important numbers may come out altered by its presence. That is why this is not really a story about emptiness. It is a story about what emptiness can do. Not in fiction, in measurement, not in metaphor, in dynamics, not as drama, as inheritance. And once you understand that, the title itself changes meaning. The void is not breaking the universe in the childish sense of ripping physics apart. It is breaking something quieter and more intimate. The assumption that the universe can be read from here without here becoming part of what is read. The universe is still lawful. The universe is still there. The universe is still, on the largest scales, one coherent reality. But the path from us to that coherence may run through a region so subtly biased that we mistook local truth for cosmic truth, and only noticed once precision made the mismatch impossible to ignore. So, the final image is not of a giant hole in space swallowing galaxies whole. It is simpler than that, colder than that. It is the image of a civilization standing inside a vast thinning of the cosmic web, looking outward, taking measurements of the whole, and slowly discovering that the emptiness around it was never empty of consequence. That the ground beneath the measurement was sloped, that the slope was real, that the number carried it, and that the universe did not have to be broken for our view of it to be. And that is the last fracture. Not that the universe betrayed us, not that physics failed, not that all the exquisite machinery of cosmology was somehow built on illusion. The final fracture is subtler than that, and harder to heal. It is the realization that reality can remain perfectly lawful while our access to it remains locally deformed. That the cosmos does not need to hide its truth to make that truth difficult to extract. It only needs to let finite observers arise inside one fold of its structure and mistake that fold for transparent ground. This is where the story has been heading from the first line. A number that should not care where we are, a region of space that may make it care anyway. A local deficit in matter large enough to alter motion, a motion field subtle enough to survive correction, a measurement clean enough to be trusted, a trust deep enough to hide the environmental tilt inside the answer itself. Every step has been narrowing toward one conclusion. The void is not just a structure in the universe. It is a demonstration that measurement inherits the conditions under which measurement becomes possible. That is the mature answer to the opening problem. Why would a cosmic void matter? Because if we live inside a vast underdensity, then the issue was never merely that our neighborhood is strange. The issue is that one of the most universal-sounding numbers in science may have been filtered through a local asymmetry so broad, so quiet, and so easy to normalize from within that we only recognized its influence when precision became too severe for the discrepancy to hide. That is what gives this story its coldness. Not destruction, not spectacle, distortion without drama. A universe can be lawfully expanding while our region expands a little more freely than average. Galaxies can be honestly receding, while also carrying extra motion from the shallow gravitational terrain around us. The nearby sky can be rich, structured, and seemingly ordinary while still being underdense enough to bias a fundamental inference. The measurement can be careful. The observers can be serious. The conclusion can still lean. That last word matters. Lean. Because that is what a local void would do to cosmology at its deepest level. Not smash it, not refute it, lean it, Tilt the path from local evidence to global truth, just enough that a universal claim begins to carry the accent of one particular place in the cosmic web. And if that is what happened here, then the Hubble tension was never only a dispute about value. It was the moment the slope beneath the measurement finally became visible. A visible slope changes everything. Not the existence of the mountain, the meaning of your footing. That is why this story should not end with a triumphant declaration that the void explains everything, because that would betray the discipline the subject deserves. The honest ending is narrower and more severe. The local underdensity may not fully resolve the Hubble tension. It may only soften it. It may account for part of the discrepancy while leaving the rest to systematics, model limitations, or physics not yet fully understood. Its profile remains debated. Its explanatory power remains contested. Its exact scale in the real universe is still being tested against surveys, flows, and simulations. All of that uncertainty is real. But uncertainty is not emptiness, and it is certainly not irrelevance. Because even if the void explains only part of the crisis, it has already done something irreversible to the way the crisis must be understood. It has exposed the observer. It has shown that the environment around us cannot always be demoted to technical clutter. It has forced cosmology to confront the possibility that local structure remains active inside the inference far longer than comfort once allowed. It has taken one of the cleanest-looking quantities in the field and reminded us that cleanliness is often the final appearance of a root whose dirt has simply been forgotten. That is the larger inheritance of this whole descent. We like to imagine that science progresses by removing ourselves from the story, first emotionally, then conceptually, then mathematically. We are not the center. We are not special. We are not necessary to the structure of the world. All of that is true and necessary, and one of the great maturities of thought. But there is another maturity beyond it. Even after the ego is removed, the observer remains. Not as a hero, not as a metaphysical exception, as a location. A location in one galaxy, inside one velocity field, inside one density profile, inside one finite epoch when the universe is still readable in the way our methods require, and that location, for all our efforts to correct beyond it, may still speak inside the numbers with more force than we expected. That is the final humiliation. Not that we matter cosmically, that we cannot stop mattering observationally. It is a cleaner, harder form of humility than anything geocentrism ever had to surrender. We gave up the center long ago. What remains is giving up the fantasy of transparency, giving up the idea that once we are no longer important, our position ceases to be dangerous. The universe has no reason to grant that second kindness just because it granted the first. And perhaps it never did. Perhaps the history of cosmology was always moving toward this recognition. First that Earth is not the center, then that the Sun is not the center, then that the Milky Way is not the center, then that our galaxy is one among billions. And finally this. Even without being central, we may still be badly placed for certain measurements, and reality does not become less universal just because access to it becomes more awkward from where we stand. That is what transforms the void from a curiosity into a worldview shift. It tells us that emptiness is not passive, that absence is not neutral, that what is missing around an observer can shape what appears true beyond the observer, that local truth can wear the mask of global truth for a very long time, and that a civilization may come astonishingly close to reading the universe correctly, while still hearing part of the answer through the contour of its own surroundings. This is not a pessimistic ending. It is a precise one, because the real wonder was never that the universe would be easy to know. The real wonder is that beings inside one local gradient, during one narrow era of observability, can get as close as we have, that from inside one fold of the cosmic web, with no external vantage point and no second universe for comparison, we can detect our own possible bias at all. We can map deficits in galaxy counts, reconstruct flow fields, compare early and late epochs, simulate cosmic structure, and ask whether one feature of our neighborhood has been bending one of our deepest measurements. That is not failure. That is almost the definition of scientific maturity. To notice the filter is all ready to step beyond it. Not completely, never completely, but enough to become dangerous to our own assumptions. And maybe that is the most honest form of cosmological intelligence available to any embedded species, not a perfect view from nowhere, not a final escape from structure, something more demanding than that. The capacity to keep discovering the terms under which our knowledge was made, the capacity to find the local grain inside what looked universal, the capacity to realize that every answer arrives through a world before it arrives as a number. So now the opening question can be answered in its grown-up form. Is this cosmic void breaking the universe? Probably not. The universe does not look broken. Its laws still cohere. Its large-scale evolution still holds together with astonishing force. But it may be breaking something we trusted more than we should have. The sense that reality can be measured from here without here entering the result. And if that sense is what breaks, then the consequence is larger than one disputed parameter. Because once you realize that the observer's environment may survive deep inside the most universal-looking claims, reality itself changes shape, not physically, perceptually, intellectually. The universe becomes less like a finished object laid open to inspection, and more like a lawful structure that finite beings must approach through gradients, inheritances, asymmetries, and conditions that never fully disappear. That is the afterimage this story leaves behind. Not a giant hole in space, not a simple fix to a famous anomaly, not a neat victory for one camp in cosmology over another. An afterimage of standing inside a vast, quiet thinning of matter, looking outward, measuring the whole, and realizing that the emptiness around you was never empty of influence. That the void may not have been tearing the cosmos apart, only teaching us, with exquisite slowness, that the cosmos was never obliged to let us read it from our own address without hearing that address speak back. And that may be the most unsettling truth of all. The universe did not promise to be measurable from where we happen to wake up.